Okay, a very good morning, everyone, and welcome to another day of HSMA training. After yesterday with your adventures in R, you may or may not be pleased to know that you are back in the world of Python today, and indeed back in the world of words as we explore some of the concepts in natural language processing that we introduced in the very first session of this module. And particularly focusing on named entity recognition, which we're going to be having a look at this morning, and then this afternoon looking at sentiment analysis. And these are two really useful approaches within natural language processing. Particularly, I mean, last year, as those of you who watched the HSMA 3 recording or attended it will know one of our PSMAs, our policing associates, did a fantastic project on using sentiment analysis on Twitter last year. A really nice piece of work. So this stuff can do some really, really lovely things. And hopefully some of you will go on and do some of this this year too. So I look forward to seeing what comes in. But as I mentioned in the very first session of this module, you may find that even if your project isn't focused around natural language processing, you may want to use aspects of some of the things that we're talking about today within your projects, because actually they're really useful ways to extract information from data, and that's basically what these methods are. It's a way in which we can automate using AI methods the information from free text data, which obviously is usually in plentiful supply, particularly in NHS settings. Okay, so let's start. And in order to start this morning, I'm going to start with a bit of a recap on some of the stuff that we talked about last time. We're not going to go deep into any of it, but just to sort of remind you of what we talked about in terms of some of the principles. So we're going to start by talking about named entity recognition. Now, let's just remind ourselves what we mean by a named entity. A named entity is a real world object that can be denoted with a proper name. And it doesn't necessarily have to physically exist, although it may. So things like me and the University of Exeter are both, hopefully, in physical existence. But it might be something that has more abstract existence. So something like discrete event simulation would be a named entity with an abstract existence. You can't physically hold it or touch it, but it exists in an abstract sense. Something like woodwork, for example, would be another example of something like that. But they'd both be considered to be named entities. And we also mentioned that there are lots of different categories of named entities, and depending on the package that you're using, the specific categories that you will use will differ slightly. But these are the ones from Spacey, and Spacey is the package that I'm going to be showing you how to use today. So remember, we had these different categories. I'm not going to go through them all, but you'll remember that we have things like, whether the named entity is a person, if it's an organization, a geopolitical entity, a product, a work of art, etc., etc. And then we've got these kind of weird ones at the bottom, which counterintuitively don't often seem as though they should be named entities, but they are. So things like dates and times and quantities, those things come up as named entities, and very often for the sort of things you'll be doing, you probably won't need them. But the point is that because Spacey will automatically identify the labels for these things, you can easily remove them and ignore them if that's what you want to do. And in fact, very often for the named entity stuff that you'll be doing, you'll probably only be interested in maybe one or two of the categories, and then you can just focus in on those particular named entities. So we also talked about a lot about noun phrases. So you had some lovely grammatical exercises on noun phrases. So we said that noun phrases are phrases that are either headed by a noun or an indefinite pronoun, or which perform the same grammatical function as a noun. So a noun phrase basically includes a noun and the modifiers which identify it. So you had lots of examples like my cat, John's cat, the cat with white stripes, the cat who ate all the tuna. They're all noun phrases. The head noun being cat in each case, and the rest of the stuff around it kind of describes that noun specifically. And then we talked about a definite noun phrase, and that's basically a type of noun phrase where the head noun refers to something specific. It's typically prefaced by the definite article, the word the, unless the specificity is contained in the noun itself. So an ordinal number such as first, you don't need the word the in front of that because the noun itself conveys the specificity. So I ran over to the dog, I sat next to the very fluffy cat, are examples of definite noun phrases, because the reader or listener knows exactly which dog or which cat you are referring to. You're not just talking about a dog or a cat or some cats or some dogs. And we concluded that the reason that we should care about this, other than the fact it's so much fun, is because named entities are found in definite noun phrases. So they're the place we need to look for these kinds of things. Now, the problem is that if we're trying to look for them in definite noun phrases, we identified a couple of problems, that we don't just refer to nouns by themselves. We don't typically say just the cat, or we might say the fluffy cat, for example. We need to pick up both. And we also need to identify what the head noun is, and there can very often be multiple contenders. So, the noun phrase "the vicar Brian" is the head noun Vicar, or was the head noun Brian? My cat Bob, the same problem. So we need to know which one is the head noun. To help us do some of this, we can do parts of speech tagging. We talked about parts of speech and how there are 9 parts of speech within the English language. And basically a part of speech, or pos, basically indicates the category to which we assign a word in the context of the sentence to describe its syntactic function. So what role is this word playing in this particular sentence? And that's known as a part of speech, and the way in which we label those parts of speech is known as Pos tagging in natural language processing. So we've got the common ones we all learned at school, things like noun, pronoun, verb, adjective, adverb, determiner, preposition, conjunction, and interjection. And in any piece of English text, any word in a document will always fall into one of these pos tags. And you probably saw in pos, doing some manual pos tagging in the exercise from the first session, that it can be quite tricky actually to do this, because the English language is not an easy one to structure, and so it can be quite a tricky thing. So thank goodness there are automated methods that allow us to do this much more easily. We also talked about the concept of parsing. So parsing is basically the process of breaking down a sentence into its component parts and describing the syntactic role of each component. And parsing is a very common thing that you do within natural language processing. So parsing, as part of the parsing process, we could identify what the noun phrases are in some text, what the pos tags are for each word, etc. We also talked a little bit about regular expressions, or regex. These are basically sequences of characters that define search patterns, which are commonly used in things like search engines, etc. And they basically describe a pattern of things that you want to search for. And traditionally, they were used extensively within natural language processing in the old days, to basically say, here, if you're looking for a noun phrase, then look for a determiner followed by an optional adjective followed by blah 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 blah. You had to set up all these patterns, and it is an absolute nightmare to do that, because the English language is so complex, and so therefore it becomes very difficult to get consistent rules that work well. But that's how you used to have to do it. And I think it's probably safe to say, after doing this a few years ago, and experimenting with it for one afternoon, if this is how we still had to do natural language processing, I certainly wouldn't be doing it and wouldn't be teaching it. But fortunately, there are much better ways now. So, I mean, the key problem with that approach, as I said, is it's a pain in the bottom. There's just so many different combinations of pos tags that could form a definite noun phrase. And we also talked about actually the real world practical problem that real world text, particularly in the stuff that you're going to be looking at, is very rarely written in kind of perfect or consistent grammar. And that approach kind of necessarily assumes that it is. So it's going to fall apart for that reason as well. So it's not only a nightmare, but it's not very practical. And so that's not a good approach. But fortunately, there is a package which you're going to play with today, a really good package in Python called Spacey. This is a really widely used package now that has a lot of credibility within the natural language processing community. In fact, most people who are into natural language processing will use maybe they use Spacey. Now, it really has sort of overtaken everything, and it's as you'll hopefully see this morning. It's because it's really easy to use, and B, because it's really powerful and it works. It just works. And we'll talk a little bit about why it works and how it works in a moment. So hopefully you've all installed Spacey by now, but remember it's just a Python package, so we can just pip install it as you would with any other kind of Python package. And we mentioned, and I'll just go over this a little bit, and I think when I talked about this in the first session, I don't think we'd done the kind of neural network stuff in the machine learning module by that point. So again, I'll just explain a little bit about this. So Spacey learns using something called a convolutional neural network. I'll come back to the convolutional bit in a minute, but let's just remind ourselves of what a neural network does. And obviously there's if you want a more extensive explanation, that we covered that in session 7D of the machine learning module 2. So basically neural networks are they use a kind of emulated structure of how the brain works, simplification of how it works, where essentially you've got neurons connected by synapses with signals being sent along those synaptic connections. So in neural network terms, what we do is we have multiple layers of nodes, and you have all of those nodes sort of connected to each other on different layers, and you've got an input layer, an output layer, and you feed in some sort of input, and it does its magic through the network and then chucks out an output, which kind of usually represents the probability of something being one thing or another. Now, basically the way in which it works is you've got a load of nodes. Each node is just doing a very simple thing. It's taking all of the inputs coming into it along all the different connections. Each connection has a weight associated with it, which kind of emulates its importance. It multiplies the input number that's coming along that connection by its weight, and it adds all those weighted calculations up, and then it spits it out the other side according to something known as an activation function. And the activation function just basically tells it how to translate the weighted sum into its output. As you saw in the machine learning session, if you one of the most common activation functions is the ReLU, rectified linear unit activation function, which basically just means take your weighted sum, so multiply each connection by its weight, add them all up, and then if the result is positive, leave it as it is and just spit that out the other side. If it's negative, then just turn it into 0 instead. And it turns out that ReLU activation function is really powerful, and just that really simple function works very well. And hopefully you saw in Mike's lecture a number of different activation functions that he talked through as well. But that's basically how they work. And the magic is that they're learning and they're back propagating. So they work out how far off they are in terms of the error, known as the loss in machine learning, in terms of how, if I'm predicting this should have been, as we gave the example, this should have been the passengers survived the Titanic, and I've predicted they didn't. Let's see which, and it uses algorithms to see which weights contributed most to it getting it wrong, and it'll adjust them accordingly, and then it'll try it again, and it basically very quickly manages to adjust its weights and get to a point where you're chucking in some input numbers, and it's getting to a reliable output, and they're really powerful. And basically Spacey uses that kind of neural network structure, but it uses something called a convolutional neural network, which is commonly used for things like image recognition too. And I think I mentioned it before, but it's basically where you can imagine, rather than chucking in all your data at once, you've basically got like a little sliding window. So you just look at a certain part of your data, and then you slide it along, and then you feed through the next part of the data. Obviously, it's commonly used in image recognition because you're basically just looking at a window of the image each time, and using the pixel values that you're feeding through. In text, as what happens in Spacey, basically what it's trying to do is it's trying to predict. So rather than using these kind of regular expression based patterns to try and work out where a particular whether a particular word is a named entity or not, what it's doing is it's trying to predict based on prior learning, given what I'm seeing here, given the word I'm seeing here, and the words that come before it, and the words that come after it, and other clues such as the pos tags of the words before and after, I predict this is going to be a named entity. So it's kind of looking, rather than getting us to try and work out what all the patterns are, we're using the power of neural networks, which, remember, we said is the main power of neural networks is to look for these hidden patterns that can be difficult for us as humans to identify. We're getting the neural network to do the hard work for us. So the neural network is looking for these hidden patterns, and it's then applying its learning to try and predict whether a particular word or words constitutes a named entity. So it's basically saying, okay, I see this set of words here, the fluffy cat. I've seen examples like this before where I've got the word cat, and I've also seen where there's an adjective before that and then a determiner. I think this is a named entity, and so that's the way it does it. Okay, so that's broadly speaking how it works. And again, if you want a more extensive, you want to remind yourself of more extensive explanation of neural networks, if you go back to the recording from session 7D, we talked all about neural networks there. But the key thing really to remember for this is that's how it's doing it. It's basically looking at the text a certain number of words at a time, and making predictions as to whether a particular word constitutes a named entity or not. And it's done that based on being trained via a convolutional neural network on lots and lots of text that it's seen out there in the wild. So text from the internet, text from large corpuses of collected works, and it's learnt where all the named entities are. And so it can apply that learning very effectively to new settings. Not just named entities, by the way. I mean, Spacey does all sorts of things, as you'll see. It can also pick out noun phrases and do all that fancy stuff too. So that's how it works. Now let's have a look at it. So hopefully you've all installed Spacey, and you'll also need to make sure you've downloaded this model. Now, basically, as well as Spacey, which is the package, you also download a model to use for Spacey, and basically the model is what I've just been talking about. So this is a pre-trained model, because you don't want to be training from scratch for this stuff. That defeats the object. You could set up your own neural network and train it to recognize named entities, but you'll be hard pressed to meet the performance very easily of something like Spacey. So what you do instead is there's lots of these pre-trained models out there, and I'll come back to those a bit more a bit later. And you basically use one of these pre-trained models, and the NCore Web SM model is the SM stands for small. So there's small, medium, and large versions of these models. The N stands for English, and Core Web, it basically just means it's been trained on some general web-based texts. And you can get different models that have been trained on different types of text, which can be quite useful depending on what you're using this for. So if you've got specialist language, for example, you might look for a model that has been trained on that kind of language in that kind of area, and that will help. And I'll show you an example of that in a little bit. So That's how you install Spacey, and then you download one of these models. We're going to use the Encore WebSM because it's the best sort of simple one for showing you for training. It's just a small model, but that's all you're doing essentially here. You're just saying use that pre-trained model that's already been trained. Much as we saw in the machine learning module where we could develop a neural network and then save it and use it later, that's essentially what you're doing here. You're loading a model that has been pre-trained and tested. So you'll see you've been provided with a file called Trump article.txt. This is a text from a New York Times article from some years ago about the firing of an FBI agent. What we're going to do is we're going to use Spacey to try and extract the named entities and their predicted categories from this news story. So what I'm going to do first, let's just have a look at this text file. Now, when you come to do this, you'll need to make sure that both the text file, Trump article.txt, and the Python file, Trump extract.py, are in the same directory. So let's just have a look at the text file. If I can find Spider, there we go. So this is what the text file looks like. So this is the news story. Okay, so it's just a standard news story as you might read online or in the paper. It's a real world news story, and basically we've got this block of free text, and what we want to do is to automatically pull out the named entities, of which there's going to be quite a lot in here, and automatically categorize them to say, well, this is a person, this is a country, this is a an organization, whatever it may be. Okay, so that's what we're going to do. So that's our text, our raw text that we're looking at, and again, you could use any raw text for this, but we're just using this as the example. Okay, I'll go into Spider to talk through this. I think will be best. So if I now open up Trump extract.py, let's have a look at the code. And hopefully the first thing that will strike you is that this doesn't look very long. And indeed it isn't. In fact, quite a bit of this is just me faffing around with printing and reading from a file. There's very little that you need to do to actually get this to get Spacey to pull out some named entities. So let's talk it through. The first thing we're going to do here, as ever with our Python code, is we're going to import the packages we need. So I'm going to import Spacey, because that's the main package I need. And I'm also going to import the model that I want. So remember, we downloaded the Encore WebSM model. We need to import it if we want to use that particular model in our code, and I am. So that's going to be the pre-trained model, the pre-trained Spacey model that we're going to use for this named entity. Okay, so the first thing we want to do is we're going to load this pre-trained model that we've imported into something known as a language in Spacey terms, and I'm going to call that language NLP. You can call it whatever you like. NLP is a fairly standard convention when you're using Spacey to call your language. So all we do, we've imported the model up here. Remember, this is the pre-trained neural network model. We're going to call that. I'm going to call the load method of that model, and by doing that, that'll load it as a language in Spacey terms, and we're going to store that language in a variable that I've just called NLP. Okay, so that now stores a language based on this pre-trained model. So we've taken this pre-trained model, the Encore WebSM model, and we stored that as a language, and that'll allow us to then use it. That's the first step. Then what I'm going to do is I want to read in the document for which I want to extract the named entities, which is this on the Trump article.txt. Again, really easy. Now this, you've seen file reading and writing before, so this hopefully shouldn't be too unusual, but you probably won't have seen it in exactly this format because we don't normally do it like this. But for this kind of stuff, actually this is usually what I want to do. So we're going to use a with statement. We're going to open the Trump article.txt. The encoding is just the encoding, the text encoding for this particular text. So I don't worry too much about that at the moment. I think if you leave that out, it will have the correct encoding for that one, but I'm not 100% sure. And remember, we open it as F, so we can now refer to F, the file as F from this point forward. Now, what we're going to do here, remember when we've done file reading before, we've typically read it in kind of line by line, or used a CSV reader and read it into a pandas data frame, or done something like that. What you haven't really done before, because for other purposes you probably wouldn't want to, but for this you do, is just basically reading the whole file at once. But that's exactly what we want to do here. So you can use the .read method of a file object. And that basically just means reading the whole thing. Just read the file, give me the whole file. And it'll read it in as a single string. Okay, and you can see why in a lot of circumstances you wouldn't want, that's not going to be very useful for you. But for this, it's exactly what we want. We just basically need to grab that data so that we can let Spacey do its magic on it. So we use the f.read method to do that, and we're also going to use the .strip method. Basically, that just it reads everything in one go, but it'll just strip out any white space at the start and end of the file. Okay, so it'll just make sure that it only gives us the text that we want. So that's just a little extra option that enables it to work nicely with Spacey. So basically, this will then read the whole file, stripping out the space at the start and end, and it'll read it into a string called raw read. Okay, so all we've done so far is we've imported the packages, we've loaded the pre-trained model that we're going to use, and we've read in this file here, and that's now all going to be stored as a single string, okay, which we've called raw read. Here, this next bit is where we're going to do get Spacey to do its magic, which will include actually identifying the named entities. So all we do to do this is we apply the model, which remember we've called NLP. We've loaded it into this language, which we've called NLP. We apply the language to the string of text that we've just read in, raw read. So we say NLP, open the brackets, give it the text we want to read. That will apply that pre-trained model language, and it will do not only extracting named entities, as I've indicated here, Spacey will do all of its parsing stuff, all of its magic, it'll do all of its amazing stuff in about half a second. Well, I mean, this is a very short piece of text, but so it'll apply and do all its magic in that way. And what it'll do is it'll store that in something known as an article. We've just called it, so it's known as an article in Spacey. You can call this whatever you like, it's just a variable, but it's, again, common convention to call this article as well, so that's very clear. So basically, we're applying the language from the pre-trained model that we've loaded, and we're applying it to this text, and basically article stores all the results of that so that we can then explore that. So that basically does it, that one line. Okay. Then all I'm going to do down here, I'm going to store the various named entity categories. So the named entities is one of the things, it's the thing we're interested in at the moment here, that will be identified by Spacey, and named entities are stored in .ents of the article. Okay, so if we say article.ents, that will give us the entities, the named entities. But along with the entities themselves, it will also give us the category. Remember the different categories of person, geopolitical entity, etc. And in Spacey, that's known as the label. So you have an entity, which is the entity itself, the text, and a label, which is the classification for that named entity. So all this list comprehension is doing is it's basically saying for each item that you find in article.ent, so in other words, for each named entity that you found in that text, give me the label, give me the classification. So note the underscore after the name here, that's very important. And that's just basically saying, go through all of the named entities you found and give me the label, the classification for it. And we're going to store that in a list called labels. So that's all we're doing there. And then finally, all I'm going to do is I'm going to print each predicted named entity along with its predicted category. So I'm just going to loop through using a for loop. I'm going to loop through using the range from the length of article.ents, which will be, if it's found 10 named entities, that length will be 10. So it'll loop through for the number of named entities that there are, and it'll print the entity itself, so whatever the entity text is, alongside the label, so what the category is. Okay, so let's just remind ourselves what we've done. We've imported Spacey and the model we're going to use. We've loaded the model into something known as the language. We've then read in the text file that we want to grab the named entities from, and we've dumped it into a string. We've then applied the loaded model, the loaded Spacey model, to that text. And then we've got this article which represents our results. And then we've just basically gone through, iterated through each of those named entities that it's found in that article to grab out the label. And we're just going to print the article, the named entity alongside the label for each one. That's it. I'm now going to run it. You'll see how quick this runs. Push F5. There we go. It's done. So you can see what it's done here. It's basically picked out all of the ones that it predicts to be named entities in this text. Now, obviously, it may not have picked them all out. We don't know its accuracy on this particular example, and that's something you'll want to check if you're running this for your own text. But let's have a look what it's picked out. So it's picked out the word Washington as a geopolitical entity. Yep, that's good. Peter Strzok as a person. Yep. FBI as an organization. Yep. Trump as a person, possibly debatable. Hillary Clinton person, Russia geopolitical entity, etc., etc. It seems to have done pretty good. That seems just flicking through that, it's actually picked out some stuff. It's even picked out stuff like last summer as being a date, which is correct. So it's done really well, and you can see, this is a model that's obviously not been pre-trained on that particular article, but it's managed to pick out the stuff very well. Now, it'll probably get a few things wrong as well, but flicking through, this looks pretty decent. And all you've had to do is these lines of text. That's it. In fact, I mean, this bit down here was just so that I could print out this. So really, it's only that's doing it. So it's quite, I think, quite impressive that it's managing to do that. And this is the power of using a pre-trained convolutional neural network model that's been trained on large corpuses of text and is very, very effective at being able to predict named entities on new unseen text, which you've just given it.
Dan.
Hello.
Hi. How complex is the code for the model, just as an idea? Because this does look very simple.
The code for the what do you mean? Spacey underlying this?
Yeah.
I have no idea. I mean, Spacey is open source, so I believe you can explore Spacey, but you don't need to. You don't need to know that. Basically Spacey is doing all Spacey's doing in effect is a version of what you learnt in the machine learning module, which is creating a neural network and then training it on very good examples and gradually refining it. And it's doing it on a convolutional version, which you haven't looked at. But basically, it's just that you're shifting it alongside along the text as you go along. But that's all it's doing. It's just doing a version of that, and it's just pre-trained on lots and lots of text, and it's done all that for you, and you can then just use that pre-trained model. So that's all you need to worry about for this. So it's good to understand how it works, so that you can understand, the basic principles of why Spacey is so effective. But that's what it's doing, and so your choice really is about which pre-trained model you might use. So this is a generalist model. So this is a general model that's been trained on various web stuff, but it's the small version. It's not been trained on as much text. So the large one, I think, is over a gigabyte in size, because it's a huge model that's been trained on lots of stuff. Did I see a hand up as well? Sorry.
Hiya.
Hi there.
Yeah, Dan, I was just wondering, so just looking at the output, you've got, sort of various people's names repeated several times and that sort of stuff. So I was just wondering whether it was, there was a way to sort of count the output. Like this person is mentioned X amount of times.
Oh, I see. Yes. In fact, you're going to do that in a second in the exercise. That's exactly what you're going to do. Yeah, very much so. So yeah. So yeah, you'll see you get a lot of repetition and stuff. I'll give you some clues in the exercise about how to do this, and there's some easy ways in which you can do that. But yeah, so basically that's kind of all there is to it. Now I'll talk a little bit after the exercise as well about how you might add to the training, and how you might expand on the training. There's ways that Spacey will allow you to add to the training yourself. It's known as sort of opening the training pipeline. So you basically can shove in your own stuff to try and improve the model for your particular context. But the basic, if you just want to use Spacey out of the box, that's it. Okay, that's all you need to do. In practice, though, obviously, as ever, as we saw with the neural network stuff, it's going to be refining stuff. So trying different models, trying different text. You might need to refine different. You may need to refine the model, so add to the training. You might want to identify what kind of words are being picked up as what kind of categories for your particular text. There's all this particular stuff that you may be looking at. But if you just want to quickly grab some named entities out, you can do that very easily. Okay. So that's Spacey.
Dan, sorry.
Yeah, sure.
There was a question on the chat actually from Thomas Knight, which is quite interesting. Is there a way of knowing whether any of the named entities were missed?
Okay, so you'd have to manually check that, because obviously, as far as Spacey is concerned, it hasn't, because remember, it's applying a neural network. So it has predicted these are the named entities. I predict these are the named entities in this text. I predict everything else was not a named entity. So as far as it's concerned, it's predicted everything. It's making the the assumption. But of course, you would want to manually check that. So the way in which you would do that in reality would be, so if this were your text, an example of the kind of text you were using it for, you'd then need to go through manually and do some sort of manual assessment. You could also cross-check it as well against other models, other Spacey models. So you could have a look at trying it with the medium model, the large model, and then have a look to see what those models pick out. Are they adding anything, or are they then getting picking out stuff that isn't relevant? Because that can obviously sometimes happen with the larger models. But yeah, you'll need to get some sense about how well that's working for your particular text. So Spacey is known to be very good for general text, but obviously for your very specific areas, what you probably want to do is have a few pieces of sample documents, if you like, that represent your kind of text, and manually verify how well it's working on that, and then use that as your estimate of your accuracy going forward.
Thank you.
No problem. Any other questions? Sorry. No. Okay. In which case, I will get you to have a go at this. But before I do that, I'm just going to flag out. So I'm basically going to ask you to do a little exercise on this, which is basically going to take what I've just done and then to extend it a little bit and play around with it and use some of the stuff that you've used before in Python, and also some of this new Spacey stuff. But also these three things here, hint, hint, will come in very useful for this exercise. They're not the only way you can do it, but this will make it much easier for the particular things I'm going to ask you to do. So the first one, this is known as the count function. You can use the count function on any iterable object. Remember, we've talked about iterable objects before in Python. They're things like lists or dictionaries, something that you can iterate through. So a list or a dictionary you can both iterate through. And basically all count does is it counts how many items match the value that you provide. So if we've got let me just, sorry, I won't expand that. So imagine we've got a list here. I've got list A. I've got the values 1, 2, 3, 3, 2, and 2. And I want to count how many 2s are in that list. Then I can call the count method of the list, and I can just pass in the value I want to count. So if I pass in the value of 2, it'll count how many 2s there are, and then I can print that, and I can see that I get number 3, which is correct. So that's a really handy little little method that you can use more generally, and certainly will be handy in this exercise. There's also something known as dictionary comprehension. You've seen and used list comprehension. Dictionary comprehension is exactly the same, but it's for dictionaries. So again, we'll use the same list here, but we're going to use a dictionary comprehension here. Now remember, in a list comprehension, we use the square brackets because that's how we denote a list in Python. For a dictionary comprehension, we use the curly brackets because that's how we denote a dictionary in Python. So what this dictionary comprehension is doing, remember, it's always usually easiest to read a list or dictionary comprehension from the 4-bit. So what this is doing is saying for each number in list A, so for each entry in list A, what I want you to give me in this dictionary, and remember a dictionary is just a set of pairs of keys and values. So I want you to give me the key as being the number, so that's the value I'll look up. And I want you to give me the count, which is that method I've used above, of that number as the value. So what that will do is it'll say for the value 1, then there give me the count of how many ones there are in this particular list. And so there's only 1. For the value 2, there are 3 of them. For the value 3, there are 2 of them. Okay, that's a handy little way in which you can quickly assemble a dictionary where the lookup value, the key, is the value that you want to count, and the value against that lookup is the number of times that value appears. Okay, so that can be really, really handy. So big hint there that might be useful in a moment. And the last thing that will hopefully prove useful for you is the collections counter. So there's a library called collections, and it's got a module called counter within it. So we can say from collections import counter. This is a really useful module because it allows us to do stuff like retrieving the X most common values within a particular list as a list of value frequency tuples. So let's again take our example list here, 1 2 3 3 2 2. What I can do, I can import this counter module from collections, and I can apply the counter to that list. Okay, so that's a counter, open brackets, list A, so I pass in the list, and then I can call various different methods of the counter module, and I'm going to here call the most common method, and I pass in the value for X. In other words, I want to grab the two most common values. If I put 5 here, it would give me the 5 most common values, etc. And then I can just print that. So in this case, it'll then return this list of tuples. Remember, a tuple is just a set of values within a pair of brackets that cannot be changed. It's immutable. And in each case, it gives me the value and its frequency. So it's giving me the 2 most common values and how frequently they occurred. So in this case, we can see by eye that 2 is the most common value because that appears 3 times, and 3 is the second most common value because that appears twice. So it's giving me the value 2 with a frequency of 3 and a value of 3 with a frequency of 2. Okay, so that's how it'll then output that. So it's quite a useful way in which you can grab the X most common values in a particular list. Okay, so those 3 things will help you for this. So what we need to do is I'm going to put you into your groups. You might want to take a 5-minute break first, and then I want you to basically extend the code in the trumpextract.py. So that's the code I just ran a moment ago. I've given you that code. Take a copy of it first, so that you've got the original copy as well. So just work on a new copy because you're going to be playing around with it. And what I want you to do is do the following. First of all, to store the named entities and their frequencies within that article in a dictionary with keys representing the particular named entity strings and the values representing their frequencies. So what you should do first is to grab the named entities. You need to convert them to strings because the named entities, the .article.ents, they are not stored as strings, so you need to cast them as strings, and then store them in a list. Then use a dictionary comprehension, which I just showed you, to create the dictionary that I'm describing here, and then just print that dictionary out. Okay. Then I want you to print the 10 most common named entities in the text that it's picked out. I want you to print the 16th sentence of the article. Remember, you're going to start counting from 0. Now, the sentences of an article are stored in article.sense. So the named entities are stored in article.ents, and the sentences are stored in article.sense. So as well as doing named entity recognition, Spacy's also chunked it up in chunking, which is where it divides up the article into sentences, so you can grab particular sentences out. I then want you to create a set which contains only unique named entity labels. Remember, labels are your categories. So if you remember back from the very first Python session, we said a set contains only unique values. So if you cast something as a set, it'll automatically remove the duplicates for you. Okay. And then lastly, I want you to print the set of unique labels to the user and ask them to select one of them. Then display all the named entities with that label. So for example, you're going to basically say to the user, here are the named entities that have been found in this text. Oh, sorry, here are the labels, the types of named entity that have been found in this text, like person, org, etc. Which one do you want to look at? So if the user typed, for example, org, then it'll then print for them all of the named entities in that's been predicted in that text to be of type org. The hint to do this: use a list comprehension to grab the named entities from article.ents. Remember, that's where they're stored. Remember to cast them as strings. They are not strings by default. Where the corresponding label, remember article.ents.label underscore will give you the category. Meet the condition you need. Then you just need to cast the list as a set to remove duplicates. And for extra points, you can put all that in an infinite loop so that they basically can keep selecting labels. So take a 5-minute break or so. What time is it now? 20 past. Okay, so I'll give you until about 5 past, 10 past 11. Have a work in your groups. In fact, let's go to 10 past. Just give you a bit of extra time. So we'll resume at 10 past 11, work in your groups, have a go at this, and just take this step by step. This will make more sense as you start to do it. Okay, let me open up the breakout rooms. Hi everyone. Okay, so I'll turn off subtitles, otherwise I end up repeating myself. I bounced around quite a few of the rooms. It looked like you're all getting on really well with this, actually, and the purpose of this was to get you used to Spacey and sort of, how it works and interrogating the Spacey outputs. And there's lots more that we haven't covered in this, but it will give you a sort of general sense about how you can look at some of that stuff. And you all got on really well, actually. You all got stuck on part 3, which is partly probably entirely my fault. I'm not sure if I was being mean or just forgot to add something in when I gave you the thing to do on 3. So probably what I should have mentioned, I've got a feeling it's one of those things I've got a feeling I said last year and I said I'd correct it. So I bet I do this again for HSMA 5, but it's nice to have a challenge. So where you were trying to print the 16th sentence, a number of you came across the problem that you tried to do that and it said you found the article.sense, as indeed article.ents is. They are generator objects in Python, so you can't just you probably got an error message saying you can't, it's a generator object is not subscriptable, i.e. you can't say give me a value at index 15. It won't work, but what you can do, which is a beauty of Python, is if you need something as a list, assuming it can be converted to a list, Python will convert it as a list. So you can just cast article.sense as a list, store it as, with your list name, and then just treat it as though it's a normal list. And that's really one of the nice features of Python, that if it can do it, it'll and it makes sense to do it, it'll do it for you. But I probably should have given you that piece of information. I'm just going to very quickly rattle through the solution. You might have done things a little bit differently, and obviously I will post up the solutions after the session anyway. But I'll just quickly rattle through this. Let me share my screen. Okay, so where's the solution? Here it is. Okay, so obviously most of this at the top is what you've been given. The only extra bit I've put in is to import the counter module from collections. So we need to put that in there. I saw a couple of people do this. Make sure that you put your import statements always at the top of your code. Very good practice. To do that, you shouldn't include them in your main body of your code. So all of that up here up to this point is what you were already given. So then the first thing I wanted to do was print all of the named entities with their frequencies. So the way I've done it here, I've used a list comprehension to cast each named entity as a string. So I've said for each named entity in article.ents, which is where they're stored, give me back the named entity but cast as a string. And I'm going to store that in my list I've called any list. And then I can set up a dictionary using a dictionary comprehension. And I can say for each named entity in any list, because I've now got these stored as strings, these are now strings. So for each string casted named entity in that list, I want you to give me a dictionary where the key, the value you're looking up, is the named entity itself. So Trump, Washington, whatever it may be. And then the value is the number of times it appears. So I'm going to use the count method on any list, and I'm going to count the number of times that named entity appears. Then I'm going to print that. So it'll print that out. Then I'm going to print I want to get the 10 most common named entities found and their frequencies. So I can use this counter module to do that. And I can simply give the counter module the frequency dictionary that I set up here. Some of you did that on the list. You can do that as on the list, but you can also do it on the dictionary itself. Doesn't matter. Both will work. So I've just passed it in with the dictionary there and asked it to give me the 10 most common. And I store that in most common. And then I can print the most common. The 16th sentence, this is the one that's where it tripped a lot of you up, so apologies for that. So all I need to do is just cast article.sense as a list. I'll store that in a list that I've called sentences, and then I can deal with that list. So I've just put here to print the 16th sentence, which of course, because we start counting from 0, is at index 15. Then I want to grab a list of unique named entity categories, so the labels that have been predicted. So to do that, I can just cast them as a set, because then Python will do its magic. Sets are like lists, but can only they're not ordered and they can't contain duplicates. So if you make something a set, Python will automatically remove the duplicates for you. So I've already got my list of labels up here that you already had that given to you, where we stored a list of labels. So I'm just going to cast that list, list of labels as a set, and that will give me a set of unique labels. Then this bit, which is the fifth bit I asked you to do, which is basically where you get the user to input one of these categories, and it'll show you all the named entities for that category, which is quite a useful little thing to do when you're exploring this. So I put everything in an infinite loop. So while true, remember that's quite a handy way to do that. First thing I'm going to do is print the named entity categories that it found. So I'm just going to loop through each label in the unique label set, that one I just created up above, and print out the label. You might have just printed the set as a single statement, that's fine. And then I've got a nested infinite loop here, which basically says gets an input from the user, says which label do you want me to list named entities for. I'll store that in selected label. If it's in that set, so I can use the in keyword, so if whatever they've put in is in this set of unique labels, then I can break out of this little mini nested infinite loop. Otherwise, I'll just print the message, no such label, please try again, and it'll keep going round until they put in something valid. Assuming they do, it'll break out of it and go back down here. And then I can store a list of named entity values for the specified category. So again, I can do this through a list comprehension. So again, with any list comprehension, it's always easiest to read it from the for statement. So for each named entity in article.ents, if the label for that named entity, so the corresponding category, cast as a string, is equal to the label that they've put in, because remember, this isn't going to be a string, so you need to cast it as a string. So basically grab the label associated for each named entity, grab the associated label, the associated category, cast it as a string, and then see if it compares to the one they've input. So let's imagine they've input org. If I cast this label for this named entity as a string and it matches org, which is what the user's input, then give that back to me, give me the named entity, but cast as a string. Okay, so again, you could do this as a for loop, but the list comprehension allows us to do this in one. So for each named entity in article.ents, if the corresponding label cast as a string matches what the user inputs, then give the named entity, not the label, back to me as a string. Once I've done that, I can then convert that to a set. So we've only got unique values, because that'll have every individual occurrence of that named entity. So again, I can just cast it as a set, and I've stored that as a set called any sub list set. And then I can just print each item in that sublist. So if I run that, X is not defined. That's helpful. Where's that? That's very odd. That should work. Let me restart.
Your first line has an accidental X in it.
Oh yes, it does. Thank you. I've obviously got excited there and typed that. Thank you. It's usually the simple things. Let's try that. That's good. That seems to be running. Brilliant. Fantastic. So yeah, the first thing, we printed out all the named entities and their frequencies, then the 10 most common, then the 16th sentence. Then we said we found the following named entity categories. You should have found there were 8 different categories that were picked up in this particular text. And then if I want to say, okay, grab me all the ones that you predicted to be an organization, I can type in org. Now my keyboard is not doing anything. That's very odd. Okay. Quite worrying that my enter key is not working. That's quite an important key when you're coding. That's really weird. Okay, I'm not sure why that's not working, but I promise you it does. And hopefully, I think most of you got nearly to that point if you didn't. Let me just... Oh, no, I can't even cancel. That's very strange. Let's turn it off and on again and see if that works. I can type, that's good. Let's run. Okay, let's try again. Hooray! I don't know what was going on there. So it just shows, turn it off and on again. The restart kernel button is a fantastic, useful thing. So if I type in org here, these are predicted to be of org category. Now you'll notice that it's got some things wrong here. So it's predicted that Trump is of org category, which isn't quite right. But it has picked up things like FBI and CIA, etc. as well. So if I type in person, it seems to have picked these up quite nicely. It's picked up Trump as a person there. So different instances of the same word can be categorized differently, and that's something you'll notice, because you also remember what it's doing is not just going on this word is a named entity. It's saying this word in this place in the sentence with this pos tag, because remember, the parts of speech of one word can differ depending on which sentence it's used in. You can have something that works as a noun or a verb, for example, depending on the different context. And to the pos tags before and after it, and the words before and after it, it'll make different predictions. So we can see there's a few issues potentially in there, but generally speaking, it seems all right. It's not too bad. Picking up dates, okay. But again, this is where you'd want to refine it, and we'll come on to a little bit of that in a moment. But hopefully you got most of the way there, and as I say, I'll post up the solution for you as well. Okay, let's plow on. So as we've just seen, the pre-trained models in Spatie are very good, and they're, you know, for a first stab, they're if you want to just grab out some named entities quite quickly, it's pretty quick and easy to do that. And it's quite good in terms of its performance, but they won't recognize everything, and there will be certain words and syntactic patterns that it hasn't seen before in the training corpuses. So there are two things that you can do to try and improve accuracy. The first is you can choose a different model. So remember, at the moment, we're just using the NCore WebSM model, which has just been trained on large web-based corpuses of text. There's the medium one and the large model, so you could try those as well. But those core models are trained on general text, so stuff like blogs, news, comments, stuff. But there are other models that have been trained on specialist areas, such as there's models that have been trained on Twitter. So if you're just looking at Twitter stuff, you may want to use a model that's been trained on Twitter, so it'll be more used to the kind of language used on Twitter. Or if you're looking at you might look at a model that has been trained on medical papers if you're dealing with a lot of medical terminology, for example. One thing I will show you, which one of the groups used last year, is something called SciSpacey. If you just Google SciSpacey, I'll put this link in Slack as well, but if you Google SciSpacey, it'll come up straight away. You install that a little bit differently to a normal Spacey model, because you install it as though it's an alternative version of Spacey. So you say a pip install SciSpacey, and there's various then different models. So SciSpacey is a version of Spacey that has been used specifically for processing biomedical, scientific, or clinical text. So you may find this quite useful. And the team that used this last year were trying to use it for looking at patient notes, and they found it much more effective for named entity recognition than just using bog standard Spacey. So you install it the same way, you use it in the same way as you would Spacey, and it's got its own little models. And you see there it's got NCore SciSM, which is a bit like the WebSM, but it's particularly for SciSpacey, etc. And you can download those individual models, and it gives you some indication about the performance, that they've tested performance, pretty good performance on a lot of these things, quite high accuracy rates for various models. So it's worth, and it's quite good. It takes you through sort of example usage and stuff that you can do with it as well. Some of this stuff that you can do in Spacey, which I haven't shown you yet, but you will see this when we come on to next year, when we the delayed relation extraction session. I'll go into some of this. You can do like word tree stuff where it shows how words are related in a sentence. They're really nice visualizations, but it gets a bit complex. So that's coming up in one of the new sessions that will be in phase 2. But worth checking if you're going to do this for things like patient notes or anything where you've got a lot of medical or scientific or clinical information, which a lot of you may have, then it might be worth considering using SciSpacey. So you could compare it against using standard Spacey as well. Okay, so that's one way you could do it. The other way in which you could try and improve things would be to essentially add to the training, and via a process known as opening the Spacey training pipeline, which sounds very exciting. Basically, as you've seen so far, Spacey uses a pre-trained model. This is a pre-trained model. You grab a pre-trained model, which is just an advanced version of the stuff you've been doing when you're building your neural networks in the machine learning module. It's just one of those that's been pre-trained. You're using one of those. What you can do is you can use one of those, and then you can say, actually, I like this model. I think it's very good for my stuff, but there's a few extra words that I think it's not picking up on. So I can try and get it to learn those extra named entities. A couple of disadvantages of doing this. The first is that you need lots of examples to get it to meaningfully pick up on stuff like that. If you've only got a few examples, there's a danger of overfitting, that it looks for stuff that's too specific to the examples you gave. And by a lot, I mean at least a few hundred. So don't enter into this lightly if you're going to do it, because remember, you're going to have to give it all of these examples. It's also, well, originally, as of last year, it was really fiddly. I mean, really fiddly to do this. There was instructions on the Spacey website for doing it. And in the training last year, I showed you how to do it, and it pretty much confused everyone. Because it's really convoluted, because you have to set things up in tuples in a particular order. About 2 weeks ago, I thought this was one of the sessions that I didn't need to change much, and so I was just looking through and going over everything, making sure everything still worked. Turns out Spacey's completely changed the process, so it broke half of the training session, so I had to completely change things. I haven't had a chance to look at how it's now doing it, but it will tell you at this link. So I haven't read this yet. Hopefully I suspect they've made it easier because the old process was horrible. It was really convoluted. It was fine once you got the hang of it, but it was really convoluted. So if you do want to do this, there'll be instructions here, which I haven't read yet, so I can't comment on them. But this will still apply regardless of what they've done to the process. You need to be aware, if you're going to do that, you need lots and lots and lots of examples, hundreds of examples at least, that you're going to need to manually label and feed in. So it's probably not the best way to go unless you really think this is the way to go for your project. Your best bet is probably to try different models and compare their accuracy, and particularly choose maybe something like size spacing. Okay, let's park the named entity recognition stuff for a moment, and let's talk a little bit about word clouds, which can be quite useful to use in conjunction with named entity recognition and sentiment analysis. Now, word clouds you're probably all familiar with seeing, if not generating, at some point in your lives. They're really useful visualizations that allow us to get a sense about some of the most frequent things that are being said in a piece of text. There's a really nice Python package called word cloud that allows you to generate word clouds really easily. And hopefully you've all installed this. You just use pip install word cloud to do that. So let's have a look at how we can use this word cloud package to generate word clouds. The code I'm going to be using is a code that a file that I've given to you as well, called wordcloudexample.py. And what we're going to do is we're going to generate a word cloud taken from a random movie review on the Internet Movie Database, and that is going to be stored. I'll show you that review in this word cloud example text .text, which is also a file that I've given to you. And by doing this, I'm also going to introduce you to a few other things in natural language processing that are important concepts, things like tokenization, stop words, and translation tables. So let's flip over to Spider. So first of all, let's show you the text. No, that's not the text. Where's the text? Have I not opened the text? Oh, yeah, it's there. Can't see it for looking. So word cloud example.text. So this is the text from which we want to generate a word cloud. This is just a random review that was taken from IMDb, and it's all been sort of posted on the same line here, but you can see it's just a review that someone has posted of a movie. Okay, so all we're going to do is to generate a word cloud that brings out the most common words in larger letters so that we get some sense about what they're saying. Let's move that over there. Okay, so as I say, you need to make sure word cloud is installed first, pip installed. The first thing I'm going to do is import word cloud from word cloud. I'm going to import two things. I'm going to import two modules, word cloud and something called stop words, and note the capitalization on stop words. That's important. That's what it's you need to import it in this way. It's how it's been named. We're also going to import the string library. The string library is a really useful library that allows us to do all sorts of fancy things with strings. So it's quite a useful one to import when you're doing natural language processing stuff, as you'll see some examples of here. And I'm also going to import matplotlib.pyplot, which you're used to using. And we're going to use this basically just to display the word cloud. Okay, as you'll see at the end, that's all we're going to use it for. So the first thing I'm going to do is I'm going to read in the text for which I want to generate my word cloud. So this file here, the word cloud example text. So I'm just going to do the same as I did before. I'm just going to use the read method on the file to basically just say read the whole file in as one string. So I've opened my file in read mode, and I'm just saying using the read method, and it'll just read the whole lot in and dump it in that string. So now in full text, will be a string variable containing a single string that will contain all of that. Then what I'm going to do is establish a set of stop words. Now, stop words are an important concept in natural language processing. Stop words basically refer to words that you want your natural language processing algorithm to ignore. Okay, and there are no hard and fast rules about which words should be ignored, but common stop words are words such as the and things like that that don't generally give you much information in terms of natural language processing. They're not very useful. The words the and may well be very common in your text, but are you really going to want to see them in a word cloud? Probably not. Okay, so you typically want to remove them when you're doing that. Not always, depends what you're doing. And indeed, for the named entity recognition, we don't do that because actually the words the and provide important clues for the model to predict where it's going to see a named entity. But for stuff like this, and as you'll see in the sentiment analysis thing this afternoon, obviously detecting the tone of a piece of text isn't going to be helped by the words the and generally, and other words like that. So what we can do is we can establish a set of stop words, and we this stop words module that we imported, we can just cast this as a set and store it in stop words. Okay, so if we do that, we've basically got a unique set of stop words now. And we're using the ones from word cloud that are they've already set up for us basically. And then what we're going to do is we're going to do a process known as tokenization. And all tokenization means in natural language processing is splitting our text up into individual tokens or words. So it tokenizes, usually based on the space character to separate into words, but you can also tokenize according to things like commas or however you want to do it. But for this, generally you're tokenizing according to space, which is the default. So what this will do is it will split this string of text that we've read into individual words, and they'll be known as tokens. And so to do that, we just take the text, the string that we've read in from the file, and we call the split method, and that tokenizes into individual words. And then I'll store that in a list called tokens. So let me just run this first bit first, okay? So you can just see what it's done so far. That's not worked because I'm in the wrong directory. This would happen. Which directory am I in? Word cloud example. Oh, sorry about this. It's because it's not in here. There it is. Why is that not working? Okay, let's try that again. That looks like it. Oh, no, I've run the whole thing now. Oh, right. Okay, let's try that again. I know what it was. Right. Useful tip. Because I didn't run the whole file and I just ran a selection, it didn't update my working directory up here. It has now because I accidentally pushed F5. And so I ran the whole file. And in doing that, it'll save the file and then it'll automatically change your working directory. But I think some of you may have run into this problem before. So if you don't do that, it won't automatically change this working directory. So it thought I was in the solutions directory. That's what it is. Okay, at least I know why that's not working. It's error between chair and keyboard. Right, so I'm just running this first bit first of all. So if I look at the variable explorer now, so all I no, because I've run the whole thing. I will clear all of this out. Right, let's start again. I'm in the correct folder. Let's do this. Let's just run this bit. Hooray! It's finally worked. Okay, so I've just run this bit at the top. So I've basically read in my file as a single string. I've set up a set of stop words and I've split my string up into tokens using tokenization. So let's have a look at this. So we can see the full text here. If I double click on that, that's the review read in as a single string. And you can see it's a string up here. The stop words, this is the set of stop words. So these are the words that it's going to ignore. Okay, so things like what, was, she's, I'm, his, very, these are words that are not going to help us, that we don't want in a word cloud, or probably don't want in a word cloud anyway. We probably don't want them for sentiment analysis. So this is just a common set of stop words that's used by word cloud, but there are different ones. Ian, sorry, yes, you raised your hand.
Hi, I just want to ask, I noticed there's some HTML tags in that bit of text.
Yes.
Does the stop words get rid of that as well?
No, but I will show you how you do that. I can't remember if I do that. No, so we don't do that on here, but in the sentiment analysis stuff, I'll show you how you can do that.
Okay.
So yes, that's a very good point. So a lot of the stuff that you get will be from the internet, and it will have HTML tags. So this afternoon I'll show you how to remove those. Okay, so we've got our stop words there, and lastly the tokens. So that's where I took that string and I split it up. So it's split it up by the space character, and you can see now we've got a list of, it's a list of 516 strings, each one representing a separate word. Now you'll notice the punctuation is still in place. Okay, so where there's a full stop or where there's an apostrophe, etc., that's still here at the moment, and we'll deal with that in a moment. Okay. So we've got these individual words here set as a list of tokens. So the next thing we're going to do is set up something called a translation table. Basically, a translation table just allows us to say, when you see this, translate it into that. So it's useful for translation, obviously. But there's a neat little thing that we can do, which allows us to remove punctuation. Don't worry too much about translation tables at this stage. Basically, just know, I'll show you how this works here. So it's a method of the string object. So we can say str.makeTrans, which makes a translation table. And we pass in 3 arguments to that. The first 2, I've just put in as blank strings, okay? And the reason we're doing that is because we just want to get to this 3rd argument here. So this is a little tip that WordCloud advises. Basically what we're going to do, so if you're using this as a translation table in its full form, you could specify in here, translate anything that had, for example, this string here, and make it this string here. Okay, and it would just translate one into the other. Okay, we're not going to use that here, but what we do want to use, this 3rd argument, when we set up a translation table, basically says, and get rid of these things. So here we're just saying, yeah, ignore this, just change empty to empty, which is just saying do nothing, basically. But then this 3rd argument, we can say, I want you to remove as well all punctuation. Now, punctuation is stored in the string library. And so we can, it actually has a list of all of the common punctuation marks. So if I type in string.punctuation in my console, you can see this is string.punctuation. So it's got all of the common punctuation marks, exclamation mark, inverted commas, dollar signs, etc., etc. So that's the list of things that it can store in there, and it's really useful because usually we want to get rid of it. So we can just say get rid of these punctuation marks. So what we're going to do here is we're setting up a translation table, which I've just called punctuation mapping table, which basically says, ignoring these first 2 things, it says get rid of, when you apply this mapping to a string, get rid of anything stored in string.punctuation, which is this lot. Okay. So then we've set up the table here. Then we're going to use the translate function, which will basically apply that translation using the translation table. And we're going to do that using a list comprehension here. So again, we'll read it from the for statement. So it says for token in tokens. So for each token that we've got stored in our list of tokens here, translate that token according to the punctuation mapping table that I've set up above, which will basically look at the token, and it'll ignore these first 2 bits because we've told it to do nothing. But what it will do is say, we're also telling it, and you need to remove anything that's in string.punctuation, which is this lot. So if in these tokens, it sees a full stop, for example, here on films, it'll remove the full stop from films. So it'll give us back a list of tokens where each token has been passed through this translation such that any punctuation gets removed. And now we've got a new list called token stripped of punctuation, which is the same list of tokens, but with any punctuation removed. Sorry, yes, there was a raised hand.
What happens with the pluralizations and the comma, where there's also an S?
I will show you. So let's have a look, because we can see in our tokens, in this token, the 8th one, index 7, trias here. So we've got an apostrophe. Let's have a look, see what happens. So let me just run this bit of code now. So this is just setting up the translation table and then applying it. So if we run that, now let's have a look at our tokens stripped of punctuation. And you can see what it's done is it's just removed the punctuation mark, and it's brought the S across. Okay, so it literally just removes that as though it shouldn't be there in the first place. It's not replacing it with anything, it's replacing it with nothingness, which shunts across everything else. Okay, so we can see now if we flip through that list, we have got all the same tokens, just we haven't got any punctuation in it now. Yeah, a couple of people raised their hands.
Yeah, what part of punctuation that token dot translate is telling it to remove the punctuation?
Okay, so what it's doing is it's saying that it's using the translate method of a string. So these tokens are just strings. Okay, if we look at the tokens, you can see it's just a list of strings basically. So we can use a translate method of a string object, and what a translate method does is it says you give it a translation table, and the translation table is the thing we've set up above, and we created a translation table, and that basically says, ignoring these first two things, I also want you to drop anything that is contained here in this list, which is string.punctuation. So what this is doing,
what else could you put there? So is that third argument always drop?
Yes, exactly that. Yeah. So anything that you put in there, you could put in a list of things, and so you could set up your own list and say, you know, drop these characters, and it'll do that. Yeah. But we're saying there's already a list of punctuation marks in the string library. Grab that list, and basically this translation table will take any string of text, and it'll it'll translate it into a string of text without any of these punctuation marks. And then here, so that's where we create it, and here is where we apply it. So we say, give me back for each token in tokens, feed it through this translation, basically. And you can see, so this is, translation tables often used for translation. So you could use this to say, here's a list of English words, here's a list of French words. Whenever you see this English word, translate it into that French word. And that's how it's generally used. But word clouds advises you can use it in this way to basically remove punctuation. Was there another raised hand? Sorry. Nope. Okay. So we've translated, so we've got rid of our punctuation. So we've now got a list of tokens, list of words without any punctuation in them. Great, we're getting there. The next thing we want to do is we want to convert all the tokens to lowercase. Again, this is a common thing that we do in natural language processing, not for named entity recognition, because again, in named entity recognition, it can use all these things like capitalizations, etc., as clues. So the fact that it's a capital letter may indicate that it might be a named entity, for example, so that it uses that. But for stuff like this, word clouds, and for stuff like sentiment analysis, as you'll see this afternoon, you typically want to make everything lowercase. Now, you can make everything uppercase if you want to, but lowercase is the convention. The point is, you don't want to treat the same word that just has, in one instance, a capital letter at the start, and one instance it doesn't, separately. You want to count them as the same word. So the common way to do that is just make everything lowercase, so it doesn't matter. Okay, so we don't count those things differently, and we can really easily do that using another string method called lower. So again, I've just got a string list comprehension here. It says for each token in our list of tokens stripped of punctuation, then basically give me the token but cast as lowercase. Okay, so the dot lower method of a string will just take that string and it'll make it all lowercase. So if I run that, we can now see we've got in our lower tokens list that we've created, got all the same tokens, but everything is lowercase now. So not only have we removed the punctuation, we've made everything lowercase. And that's really important to do that for most natural language processing stuff, because otherwise you'll get words, because remember, a Python string is essentially a list of characters. That's how it treats it. So if it sees the word cannot with a lowercase c and cannot with an uppercase c, it sees those as two separate strings, because they are. One string has the uppercase character c and one has the lowercase character c. So generally, except for named entity recognition, where this stuff's important because it helps where it helps Spacey to identify things. For other stuff that you do, like sentiment analysis, you want to convert everything to lowercase. So we've got rid of punctuation. We've basically split up our text into individual words. we've got rid of punctuation, and we've made everything lowercase. Now what we want to do is basically shunt everything back together again. We want to put it back into a single string so that word cloud can do its magic. And we can do this using the join method of a string object. And what we can do is we can put, it's quite a useful little method that basically allows you to say, you can give a piece of a string. Very commonly you use the space character. So I've just got inverted commas around a space character here. And then I can call the join method on that string and feed in a list of strings that I want it to join together using this. So basically what it'll do is it'll take this list of lower tokens here and it'll join them all together into a single string, and it'll use this as the character or set of characters, you could have more than one character, to join them together. So if we use a space here, it'll basically join them all back into one single string, and it'll put a space between all of them. Okay, so if I run that, you'll see it work. So now if I look at join string, I've now got a string of text like I had in the first place, but all of the punctuation has been removed and everything has been made lowercase. So it's now ready. This is all the preparation work that we want to do in order to feed it into the word cloud. Okay, so we've basically split it up into individual words, then removed the punctuation from each word, removed the made everything lowercase, and then put it all back together. So we've now got a lowercase string. And then we can generate our word cloud, and it's really easy to do this using the word cloud library. So what we do, we've imported the word cloud class from word cloud, so we can create a new word cloud. And I've called mine word cloud rather imaginatively here, but you can call it obviously whatever you like. And there's some things I'm going to pass into it. So I'm going to pass in a width and a height. So that's the width and height in pixels of the word cloud. I'm going to pass in a background color. So what color I want my background to be for my word cloud. I can give it the stop words that I want it to ignore. And remember, I called my stop words stop words. So I've just said stop words equals stop words. So it'll tell word cloud to ignore those words when it's generating its word cloud. And I've specified a minimum font size of 0.10. Now a minimum font size of 10. So whatever font size you put in here will determine the words that get generated, because basically anything that the word cloud generates where the words come up so infrequently it would generate words that are lower than that font size, it just won't generate them. So if you wanted more words generated, you could lower the font size, and then you'll get more unimportant words, or less frequently used words, I should say, that are put into your word cloud. So be aware of that. That doesn't just rescale it. It essentially says, don't give me any words that would be generated with a font size less than this. So there's a way of having a threshold, basically. So we pass all that into the word cloud to create the word cloud, and I call once I've created that word cloud, I call the generate method to generate the word cloud, and that will allow word cloud to do its magic. And the thing I pass into that is the string of text from which I want it to generate a word cloud, which, remember, we generated up here as our join string. So where we joined all of our lowercase and punctuation removed words back together. So that will generate a word cloud, creates a new instance of word cloud and generates one from our string of text. Then all we've got to do is plot it, and we can just use matplotlib. And all we're doing is using something called the imshow method, which basically we're using matplotlib just to display the word cloud. That's all we're doing, because the word cloud itself has been generated up here. So we use here, we can set the size of the figure that's going to be generated. We turn off axes, because matplotlib by default will have an X and Y axis. We don't want that in a word cloud, so we can use this command to turn it off. And then we can use the imshow method and pass in the word cloud, and it basically just says to matplotlib, show this image, which has been generated up here. And then I've also put in a little command here just to save that figure, so I can save that word cloud as a PNG file. So if I run this entire file, let's give it a second to wear up. There we go, it's done. If I now go into plots, we can see that the word cloud has been generated. In fact, if I go into the PNG, you'll see a little bit better. So we can see here the word cloud has been generated based on that text, with the larger words coming up, which are more frequently used. So words like film and time and train, world, character, etc. And then less frequently used words, things like succeeded and betrays, etc., coming up smaller. Okay. So that's all there is to it. And you can generate a really nice little word cloud. You can play around with the visualizations of it, change the colors, change the minimum font size. So I'll show you that minimum font size. So if I were to change that, let's say I had the minimum font size as size 20, so double the size, that should cut out more words. So if I generate that again, let's give it a second to do that. And I'll go back to the PNG. Okay. And you can see it's cut out more words now. No, it hasn't. Yes, it has. So it's cut out more words. So some of the words that came up that were tiny before, like betrayed, it doesn't look like they've now come up. Okay, so that's used as a kind of threshold to say basically how much information do you want on this word cloud, because you might want a word cloud that only has, you know, the most frequent words, and you're not interested in less frequent words. Okay, any questions about any of that? No. Okay, so what I want you to do, apologies, we've overrun a little bit. So what I'm going to do, I'm going to give you, you would have originally had 50 minutes, but I'm just going to give you to the end of this session to work in your groups for this, but feel free to continue this after. So I've given you a text file called article exercise2 article.txt. Let me just bring it up. Here we go. So this is a text file, and this is basically taken from a news story that was on our website about some work a few years back that Sean and Kerry did with one of our HSMA alumni at Devon Partnership Trust. So what I want you to do, there we go. I want you to take that file. I want you to use the techniques that I've shown you. So named entity recognition that we showed you earlier, the counter library, the word clouds that I've just shown you, to generate some insights about this text. Okay, and you should refine your approach as you go. So for example, are you finding that there are named entities that you're picking out that are less relevant? So maybe it's picking out things like dates and stuff that you're not really interested in. You might want to exclude them. Are there types of words that are commonly being classified in one type of named entity that might be useful to know for future reference? What are some of the most common named entities that you're seeing, and some of the most common words, excluding stop words? Can you try and improve your word cloud visualization to be insightful but clear? So I'm going to give you to the end of the session, and at the start of this afternoon session, so just after lunch, I'm just going to ask one or two groups just to quickly present what they've done on this. Okay, so have a go at this. Just have a play around, basically. Use the named entity recognition stuff that I showed you, and also the word cloud stuff that I've shown you, to see what you can generate, some interesting visualizations, some interesting insights from this text, from this news story from our website. And I'm interested to see what you come up with. Okay, I will stop recording and I will open up the groups. So have fun, just have a play around with this. Okay, good afternoon, everyone. Welcome back. We had a bit of a break over lunch after the named entity recognition and word cloud stuff this morning. I know I did say I might pick on a couple of groups at the start of this session. I think I won't, partly because I didn't give you that much time, because obviously we were short of time, and also because I don't want to overrun this afternoon, because I will be honest with you, probably this is the hardest session of the course. Not to put you off, I'm flagging that up now because I mainly to say that I don't expect you to fully understand everything that we do and all the code we go through this afternoon. It may take a few sort of run-throughs, but hopefully you'll get the general gist of what we're doing this afternoon. So I wanted to make sure we've got enough time to go through things properly. Partly it's the most complex because it kind of builds on the neural network stuff you were doing in the with my session and Mike's sort of lecture, but it adds on some complexity because the stuff that you need to do for text-based stuff that's a little bit different, but hopefully you'll get the general gist of things. But I flagged that up mainly because I don't want you to sit there and worry and think I'm not getting this. I would be amazed if any of you got this fully on the first pass, so don't worry. And I've designed this to build around that and to give you a chance to sort of get your heads around it a little bit. Okay, so this morning obviously we talked about named entity recognition and word clouds, and you saw named entity recognition actually was pretty easy to do using Spacey. And the word cloud stuff's really nice and quite simple to do. And a lot of it's just pre-processing your data, as ever with these things. And we saw that out of the box. Spacey's pretty good with that kind of stuff, not bad at all. Make some mistakes, but obviously there's ways you can improve that, either by using different models or by adding to the training, or maybe even a combination of the two. But certainly, you know, if you wanted a quick and easy, somebody gave you some text data and said, I need to grab out all the people mentioned, I think you could pretty quickly knock something up that would be half decent, and then build and refine it from there. So that's always a nice thing, I think. But this afternoon, we're going to talk about sentiment analysis. So this is a really interesting area where essentially we're trying to use a neural network-based structure in order to predict whether the tone of a piece of text. And this morning, obviously, when we looked at Spacey, we were basically using pre-trained models, so we didn't have to worry about the neural networks other than understanding how they got trained in that way. But this afternoon, we're going to be building these networks, and it'll be no different to what you were doing in the neural network session of module 7. But there will be some differences in terms of the way in which we, particularly the way we pre-process text data. But I will walk you through all of that. So don't worry, you're in good hands, and don't panic about this. And the good news is, if you can get through this one, tomorrow, if you're coming on to the agent-based sessions, I think the agent-based stuff is really well, I wouldn't say easy, but it's certainly quite nice to get your head around. It's much more like the SymPy stuff, maybe even a little bit easier than that actually, and it flows quite nicely. So hopefully it's all a little bit easier from here. Okay, so hopefully you've all already done this. If you haven't, I probably wouldn't go doing this during the session because it's quite a large file to download. But basically, it's this is a large movie review data set that is used for at Stanford for training in sentiment analysis, and it's basically a set of 50,000 files that contain individual reviews from the Internet Movie Database, all separated nicely into positive and negative examples and test and training sets. So it's really good to do this. And what we're going to do this afternoon is we're going to try building a model that will and we'll train it on this data to see if we can build up a sentiment analysis neural network that will be able to predict whether a particular review or a piece of text is positive or negative. So just say if you haven't already, make sure you've it takes quite a while to extract because there's a lot of files on there. They need to be extracted in the same directory as your .py file py files for this session. So if I show you in my, obviously your folder will look a little bit different, but it should be this folder should be in the same folder as whatever, wherever your .py files are, basically. But we'll come back to that. Okay, so let's just have a very brief recap. We did mention a little bit about sentiment analysis in the very first session, so let's just remind ourselves a little bit. So sentiment analysis basically uses AI-based methods to try and automatically identify the sentiment or tone of a piece of text to identify if it's positive, negative, or neutral. So obviously in the machine learning module, you were looking at the Titanic data and essentially trying to say, given these features, can we train a model to predict whether a passenger that it hasn't seen will survive or die, and can it do that accurately? Here we're doing the same thing, except this time we're saying, can we train it such that we give it a piece of text that it hasn't seen and it can accurately predict whether the author intended the sentiment of the text to be positive or negative or maybe neutral. So also in a similar way to, we looked at Spacey this morning, which is basically trying to use AI to predict whether something is a named entity or not. Here the outcome is it positive or negative, and typically we use an output value of 1 to represent positive and a 0 to represent negative. Sometimes we also look at positive, negative, and neutral, in which case we'd use 1 for positive, -1 for negative, and 0 for neutral. We won't be looking at neutral stuff in this session, and to be honest, I think it's of limited utility, and I'll talk about why I think that's the case a little bit later. I think it's of limited utility for the stuff you were doing anyway. So what are some potential applications? We discussed a few in the very first session of this module. We talked about it could be really useful for automatically classifying user survey data, analyzing reviews. We can look at social media posts and flag up any negative comments or indeed positive comments to be addressed, as much as Mike Hill did last year. We can look for positive or negative reference to our organization on websites, etc., etc. So wherever we are interested in identifying sentiment and how people feel about something, sentiment analysis can be really useful. And it's often useful in conjunction with things like named entity recognition, because you can combine the two and say, okay, well, these people seem to feel positively about stuff. These people seem to say feel negatively about stuff. What are they talking about? What are people who are talking negatively about our service saying? What are the kinds of things they're bringing up, for example? And then that might allow you to address it. So the overall process for sentiment analysis is as follows. Some of this is a little bit different now to how it used to be in newer versions of TensorFlow, but what's going on under the bonnet is the same principle. So I'm going to talk about what's going on under the bonnet so you can understand what happens. It used to be some of the stuff you had to do completely manually. Now it takes away some of that, but you still need to set up the options. So you still need to know what's happening. But the broad process is you basically load in some raw text data, the data that you want to train it on. You clean it up in some way. You convert the clean words into numbers, and I'll come back to that. We convert it into a format that's usable by a neural network. That's a tensor, if you remember from module 7. We then build the neural network, we train the neural network, and then we use it, assuming it's performed and trained well, we use it to try and predict sentiment of new data. So in terms of cleaning the data, when we're doing sentiment analysis, and I touched on this morning, there's a number of things that we have to do first to try and clean up our text. And we don't tend to do that with named entity recognition, because actually with named entity recognition, as I mentioned, things like whether a capital letter is present or not, or stop words like and the, or she, or whatever it may be, they might be important clues to try and work out whether it thinks something is a named entity or not. So we tend to leave everything in and cast our net wide when we do named entity recognition. But for stuff like sentiment analysis, that's not going to help us determine sentiment. The word and tells us nothing. For example, the fact that somebody's put a capital letter, unless they were talking in exclamation, sort of putting everything in capitalized, although again, that could be an extreme sentiment in either direction. So it's not really going to necessarily help us. So we tend to look more at kind of certain keywords when we look at sentiment analysis, and less about the actual formal structure of the text. So there's a number of things that we typically want to do with our text data before we plug it through a sentiment analysis algorithm. And these are the 5 key things that we tend to do. First, convert everything to lowercase. We saw an example of that before lunch. For example, we don't care if someone wrote rubbish or rubbish with a capital R or lowercase, or even weird typos online. They could have had capital letters all over the place. Doesn't matter. They mean the word rubbish. That's all we're caring about. It's the word rubbish that is giving us information, the clue to our sentiment. So we want to consider all of that in the same way. Sorry, yes, got the raised hand.
Oh, hi, sorry. Well, what if we do care about the casing of the word?
Why would you, sorry, for sentiment analysis?
In like internet culture recently, there's like a meme where people capitalize random letters in a word to indicate sarcasm, for example.
Oh, okay, so that could be, so yeah, absolutely. So maybe that you've got something like, and that's an interesting point actually. So the Mike Hill, when he did his project last year, one of the things he was doing, obviously he was working on Twitter, and he tried to do a bit of sarcasm, quite successfully I think, tried to do a bit of sarcasm analysis, which is really hard, as we touched on the first session, by trying to look at the way in which people use certain emojis. And so he did a little bit of that. So rather than just removing the emojis and ignoring them, which he did initially, and then he started bringing them in and seeing if that gave him indications of when people might be being sarcastic, when you sort of analyze the sentiment of what they've said, and then look at the emojis they've used, and are there contradictions? Does that possibly imply sarcasm and things like that? So yeah, I mean, so yeah, maybe if there's stuff like that, you could leave that in and see if that helps, or do something a little bit different with those words. Certainly. I think there was another raised hand. Sorry,
Dan. I was just wondering whether it picked up spelling mistakes. So, like you could spell rubbish. Like when I read this, I read the capital I as a lowercase l.
Oh, I see. Yeah. So no. So basically, what it's going to do, obviously, if somebody did write the word L there, with an L instead of an I, it's going to pick that up as a separate word. But I'll come back to why that won't matter unless everybody is a terrible speller a bit later. So you'll see why it basically filters through the noise. So it will pick those things up separately, but the importance of that particular spelling mistake will be reduced to nothingness essentially. So yeah, we'll come back to that. Okay, so that's the first thing we want to do. Generally, we want to convert everything to lowercase because we want to basically consider everything as the same word. One of the other things we want to do is we want to tokenize the text. So we saw that before lunch, where we're basically just fancy way in natural language processing of saying we break down our text into a list of individual words. Because remember, with sentiment analysis, we're not in. So with named entity recognition this morning, we were putting everything through in the structure that it was. And maintaining that structure, because the structure is important because it determines the pos tags and the order of the words, etc. But for sentiment analysis, it's not. You're basically trying to grab out certain keywords. So the structure doesn't matter. So we actually want to break our text up into words so that we can focus on certain words. We also want to usually remove punctuation. It doesn't tend to help us, although again, you could argue emojis are a type of punctuation essentially on in social media, and so there may be instances, as Mike discovered, where that might be quite useful. And again, you can do or not do any of these things. Sometimes you also want to remove numbers, depends what you're doing. Sometimes you might want to try both and see if they give them any clues. Typically you tend to remove numbers. It doesn't tend to help you on its own very much. Those things tend to not be that useful for determining sentiment. As I say, numbers might be, depends on the context. It very much, all these things depends on what you're doing. Another thing we want to do is something called word stemming. So let's consider the words watching, watch, and watched. All of these words, they are different words, but they all have what's known as the same stem. In other words, they all have the stem of watch. And they're just different tenses of that word, and so it doesn't really matter if somebody said watching, watch, or watch for the purposes of sentiment analysis. It's actually the stem of the word that we're interested in. So rather than having lots and lots and lots of different words, they're all just variations of the same word, the same meaning. We can use a process called stemming, and we can treat, in this example, all three of those words as the same word semantically. And that helps us because we don't want to have lots and lots of separate words that we're having to deal with. We want to try and identify what are the key things that we can get information from. And lastly, one of the things we usually want to do, as I say, is remove stop words. As we saw this morning, for the word cloud stuff, it wouldn't be useful for that. And for sentiment analysis, it will rarely help us. So removing stop words is a very common thing that you would do when cleaning your data for sentiment analysis. Okay. Now, I think I mentioned this before in the module 7 stuff, but when we talked about neural networks and computers in general have to deal with, at the fundamental level, numbers. They can't deal with text. Everything has to be essentially a number. And so when we build a neural network, we can't just push through text. We have to, in some way, convert our text into numbers. Because the neural network can't remember what a neural network's doing. It's essentially just loads of nodes that are taking weighted sums, adding them all up, and then chucking them out the other side according to an activation function. Well, it can't do that with words, so it needs to do it with numbers. So we need to find a way in which we can convert our words into numbers meaningfully, such that the neural network can then manipulate those numbers, and that it can get to an output value between 0 and 1, which will indicate whether it's more likely to be positive or negative. So the common way in which we do that for sentiment analysis is we represent words as numbers according to the inverse of their frequency in the text. So the most frequent word in a piece of text would have a value of 1. We'd use the number 1 for that. And the reason we do that and do the inverse of the frequency is it allows us to easily chop out very infrequent words. So we could then say, look, we're only interested in the 10,000 most common words. So then we can just say any words with a value more than 10,000, just drop them. So it allows us to easily do that. And so that's why it's commonly done in that way. Because actually, if we've got really infrequent words, they're probably not going to help us, because we need to learn from lots of examples, and there's not going to be enough examples for us to learn anything meaningful. And what we'll end up doing, if we're not careful, is just overfitting to the training set. So we typically want to take out a chunk of words that are the most frequent. It still may be, like 10,000 words. There'll be a lot of different words. And remember, these aren't just words. They're M&S words. No, they're STEM words. So things like, watching, watch, and watch will be counted as one word, essentially. So 10,000 is quite a lot in that context. So as well as converting it into numbers, our text into numbers, once we've done that, we also have to convert it into a format that is acceptable for a neural network. And the ways in which we do that, we have to separate the data, and you'll remember some of this from the module 7 stuff. We separate our data into inputs, which is essentially our features, and outputs, our labels. But in the case of sentiment analysis, because we're dealing with text, the inputs are the sequences of words, remember, but they're now numbers. So you might have a sentence might be represented as 3, 7, 27, 402, and each of those represents a word, essentially. And that will make up the bit of text we want to classify, and our labels, which will be a 1 or a 0 to indicate whether it's positive or negative. So essentially, you've got a list of numbers that represent various words, and then remember, it's a labeled data set. This is supervised learning. We're showing it some examples and saying, well, that combination of words, that was a positive review. That combination of words, that was a negative review. We also, if you remember from your neural network stuff, we need all of our inputs to be the same size. Now, that obviously, when we're dealing with something like the Titanic data, that's not so much of a problem, because you've just got maybe some empty columns and you can do something about that. But you have to do the same thing with text. Now, text can be more problematic, because if you've got Titanic data and you've got, I don't know, 20 fields that capture, 20 features that capture various pieces of information about passengers, You may have some missing data, and you saw that in the Titanic data, but you can do things to try and estimate what some of those missing fields might be. However, with text, we would expect things to be all different sizes, because not everybody writes exactly the same length review, for example. In fact, they could be wildly different. You could have a 5-sentence review versus a 5-word review versus a 2,000-word review. So that's potentially a problem. So the way we deal with this in text data is we decide on a size, a length, a number of words, and anything longer than that, we truncate, we chop off any reviews that are longer than that, so we only look at that number of words that we specified. And anything shorter than that, we do something known as padding, and we use a dummy word value of 0. And what TensorFlow will do is it will treat that as as emptiness, basically. It won't do anything with that. It'll just accept, okay, I don't need to do anything with it because it's a 0, and therefore I'm not going to get any sentiment from that. And if you think about it, that would make sense, because the zeros aren't going to do much in terms of your weighted sums as you go through. So that's why we use padding. So you decide, basically, and this can be a bit of an art. So in the neural network stuff in module 7, you saw that the things you could play around with in the network. When you're doing it for text, this is one of the things you can play around with. Do we want to include more longer reviews? But then the danger is that you're increasing the amount of reviews that got padding, or the amount of padding on those reviews, and you're potentially then running the risk of overfitting, because you're picking up on stuff that may not matter. But at the same time, maybe you're not capturing enough by you've got, your review lengths are too short. So there's no hard and fast rules. You just have to play around and see what works for your particular data. And then, of course, we want to split our data. Then this is something you will be familiar with, into training, validation, and test sets. Remember, if we split it as a training, validation, test set, then the neural network is learning from the training data whilst taking a peek every now and then at the validation data. So it's kind of a sneak peek at some other stuff to help it adjust itself. And then once it's done and once it's fitted, we can then test it out on the test set, which is not seen before, and it can test out how well it performs on data that it's not been trained on. When we come to build and train the neural network, what we basically want to do is we want to build the neural network up one layer at a time, and you saw that in the module 7 session, where you're just gradually building up a neural network one layer at a time. And then we compile the neural network to assemble it. And then we also want to specify, and again, you saw this before, how many epochs, which remember are kind of our learning time units. An epoch represents all of the data has gone through the network once. And so how many times does it need to do that? You always need more than one, because the first time will be dreadful, as you see, because it's just got random weights. But then it very quickly usually improves. So we specify how many epochs we want. Also the batch size, again, you saw that before. That's basically how many inputs you shove through the network at once. You tend to not want to put everything through at once. That's usually bad practice. So finding a good batch size is, again, that's an art form. People disagree on stuff like that. I think, well, in this training, we'll be using a batch size of 32. I'm pretty sure that's what Mike advises as well for the machine. I can't remember if it's 32 or 64 he uses, but that's the kind of area you want to be looking at. But again, something you can play around with in your data. Then you start the model training itself. Remember, that's called fitting. And then we output metrics so we can see how well it's learning, and also look out for overfitting, all the same as you did for the neural network stuff. Okay, so I'm going to show you in a second an example of this code. I'm going to talk you through an example of building a neural network that we can use for this data that you've downloaded. We're going to use TensorFlow as we did for module 7, the Google thing. I'm going to use the Keras API to make that much more friendly. But before I show you that, I'm going to just briefly talk you through what the code is going to do first. So here's the directory structure for the examples. So the data you've downloaded is split up in this way, where you've got a test folder and a train folder. And then within the test folder, that's split into two other folders. One says neg, one's called pos. Same with the train folder, we've got a neg and a pos. And then within those, each of these 4 subfolders, you've got a series of text files. And each of those text files represents one review from the Internet Movie Database. Okay, so there's 50,000 of them in total across this, and you've got a separate .txt file for each review. In fact, if I show you, let's come out. Let's have a look. So we see, ignore this bit. You can see we've got test and train. If I go into the training set and I go into neg, and that's going to take a second to load. You can see you've got loads of text files. If I just bring one up at random, story of a man who has unnatural feelings for a pig. Okay, that's an odd one to start with, but we can see it's probably going to be a negative review. So these are all ones that have been labeled as negative, and then in here will be ones that have been labeled as positive. So these are, anything about pigs here? No, that's all good. These basically, it's all been separated out for you, and we're going to use this as our training data, and then the test data that we'll test it on is in here, and that's split up in the same way. The reason we do it like this, and the reason the data set's been set up like this, if we set up our structure like this, as you'll see in the code, we can use a really handy little utility that automatically recognizes, oh, that's your training data, that's your test data, those are negative examples, those are positive examples, and we can skip a lot of the stuff about reading it all in and doing all that. It does all that for us, and it makes things much easier. So splitting up your data like that is now the recommended way to do it, and that's why that data set is split as such, and you'll see that in action in a moment. We're going to split into training, validation, and test sets. Remember, so we've already got a training set and we've got a test set. What we don't have is a separate validation set. So what we're going to do is we're going to take a portion of our training data that we've just seen, and we're going to carve that off, and we're going to use that as the validation set, which it'll have access to while it's training, and it'll peek at it every now and then to try and fine tune itself. We're then going to go through a process of standardization, vectorization, and embedding. So the standardization bit is kind of the bits I was touching on a minute ago, where you're doing stuff like removing capital letters, removing punctuation, etc. I'll also show you, so you can remove HTML tags. I'll show you how to do that. We saw that this morning, came up in some of the text. So eventually we get to, from our sort of raw web-based text, into some text that's got removed all its punctuation, it's all lowercase, it's got rid of the HTML tags, etc. Once we've got that, that then gets turned into numbers, and that's the process known as vectorization. So we turn each of these words become numbers. So maybe the word "the" is, well, actually we would have removed stop words. To think about that, but bad example. But imagine these are our words, so that would be that translates to the word 3, movie to the number 72, was to the number 5, rubbish to 763, and then let's say that we've got a review length of 7. That's a pretty short review length, but that's all I could fit on my screen. And so in this example, the rest would just be filled in with zeros. That would be the padding. So that's the vectorization process, and they will represent essentially the inverse frequency. So the higher the number, the less frequent that word appears in the text. Once we've vectorized it, we will then embed it, and that's basically the process of putting it in the shape that it needs, the tensor, remember, for a neural network, to go through the neural network. I'll show you a couple lines of code that do that. Don't worry about what it's doing. As I said, tensors are complex, so don't worry too much about it. Just know I'll show you how to do it. So remember, this is once we've done all that, we're going to build up our neural network. Remember, a neural network is made up of loads of nodes that are all connected in some way. Each node is just taking a weighted sum of the inputs, and then it's spitting it out the other side according to some sort of activation function, which if it's just a ReLU activation, it will just spit out a positive number, and if it's negative, it'll turn it into 0. And then we're just connecting loads of these together, and we're building them up in layers. So we've got an input layer. That's where our tensor gets fed into. Remember, our tensor is going to represent our numbers, which represent our words. That gets shoved through into the input layer, and then it gets all through these hidden layers in the middle, and then we'll have an output layer here, which will present our output or probability of it being positive or negative. And we may also have dropout, and you'll see some examples of dropout, which is where you're essentially randomly turning off certain nodes, certain weights within the network. to prevent overfitting. So I've touched on that. Okay, so let's have a look. So brace yourself. This is a very long file. It's not quite as bad as it looks. The reason it's so long is mainly because I've put so many comments in it. And the reason I put so many comments is because I want this to be easy for you to go back and read and understand what it's doing. Okay, so actually, if you scroll down through, you'll see quite a lot of it is comments, and actually the code, I mean, look at that. The code is actually fairly minimal, or certainly, not too bad. So don't be put off by the size of this. A lot of this is comments to help you understand this. Okay, so and once you get into the swing of this, you'll be fine. Trust me, it's not too bad. And certainly the neural network stuff you did last time will help you with the general process. Just there's a few differences because it's text we're dealing with. So this stuff up here just tells you about all the pip install stuff. That's what I've told you to do ahead of this session, and about downloading the large movie data set. Yeah, okay, that's fine. So the first thing we need to do, as with all of this stuff, we're going to do our imports. So just flag out, so we're going to import a library called RE. This is a library that's used for regular expression functions. We do have to use a regular expression in here. I'm not going to go into detail about it because I hate regular expressions, as most sane people do. So I'll just show you it. I'll just say copy and paste that when you need to use it. And that's as far as we'll go with regular expressions. I think that's good. We're going to import the string library, which is a library for string functions that we used earlier as well for the word cloud stuff. We're going to then import TensorFlow as a TF. So much like NumPy and Pandas have their aliases, TensorFlow has the alias TF, and various bits of Keras, which is the API that we use to access TensorFlow that we need. So these things here: layers, losses, pre-processing, and something called text. So this stuff you'll be used to seeing, but the text vectorization stuff is a bit different. That's going to help us do the turning the words into numbers stuff without having to do it manually, basically. Okay, let's begin. Deep breath. We'll take a sip of water. So remember, we just talked about when we push data through a neural network, we don't want to push everything through at once because it will lead to an overfitting nightmare. So we tend to avoid that. So we want to split it up, our data, into batches. And initially, I would just advise starting with a batch size of 32 and then maybe playing around with it. It's one of the things you can play with in terms of the model to see if different batch sizes work. But I wouldn't deviate too far from that. In fact, general rule of thumb is that 32 or 64 is about the size you want to go for this sort of stuff. So start with 32 is the general rule here. So that's where so I'm going to store my batch size there. I'm not doing anything with it at the moment. I'm just setting up. So if I want to change that, I can just change it here. We're also going to set up a random number seed. So for those who aren't aware, when we generate random numbers on a computer, most of the time we're talking about pseudo-random number generation, where it's not actually generating truly random numbers. Just to say, it doesn't matter. It really doesn't matter in most cases. What it's actually doing is using a very complex algorithm to generate numbers that appear to be random. But that also has the advantage that you can input a random seed. That basically tells it fixes the algorithm so that every time you generate random numbers with that seed, you'll always get the same random numbers, which exposes the fact they're not random. So it's useful for training, obviously, because you can all get the same results, but it's also essential when we're using a validation split and shuffling the data, as we're going to be here, because we need to ensure there's no overlap between training and validation. We want the training and validation to be separate. And if we keep shuffling it and we haven't set the seed in place, basically it'll start overlapping and it'll start training on stuff that you shouldn't be looking at all the time. So don't worry about it. I mean, that number could be anything, but just leave it as 42 for the purposes of this, and you should get the same results. So then what we're going to need to do, we talked about the reason we've set up our directory structure, our data, such that we've got it split into train and test, and then pos and neg subfolders, etc. And the reason we do that is, I said we were going to use this fancy little feature. Here is the feature we're going to use. It's called the text dataset from directory. and it's part of Keris's pre-processing module. And this is going to do all the magic for us. This is going to save us a lot of headache by saying, here's my data, look, here's my training data, here's my test data. It's split into negative and positive examples. Do your thing, give it to me in the format I need it for this, and it'll do that. So that's why we do it. So what we're doing here is we're using that. And the first thing I'm going to do is to set up my training data set. So here I'm setting up my training data. I've just called it raw train DS. I'm going to tell it to grab it using this text data set from directory utility. So the things I'm going to need to pass into that are the location. So that's the file location, ACL IMDb / train, which you'll see is what it is, ACL IMDb and train. That's where our training data is. Okay. We'll tell it the batch size, which I set up here. I could have put 32 in there, but it's quite good practice to separate that out so I can change it easily. I remember I want a validation set in here. So we've only got training and test data, but this allows us to easily just split off 20% of it as validation data. So if I put 0.2, it'll take 20% of it at random, and it'll make that the validation data. But I say that this subset that I'm talking about here, that I'm storing in this variable, in raw train DS, this is going to be the training bit. So I say my subset equals training. Say what I'm talking about in this, I want you to shove. So take off 20% of it for validation, but the remaining 80% is going to be stored here. And the seed, if you've got one, which we do have here, we need it. Just use that number up here, which again I could have put in 42 down there if I wanted to. So that sets up our training data basically. We can then, the advantage of doing this is that we can then print a little message and we'll see the way in which it's automatically allocated a label of 0 for anything that's negative and a label of 1 for anything that's positive. So let me just run. Oh no, I need to run up a little bit, won't I? Let's just run from the top. Just run this bit a minute. Of course it was going to do that. Of course it was. It's because I've done the same thing I did this morning. I need to change my working directory. Sorry, I keep saying you need to do this and then I don't do it myself. Okay, now that should work. Here we go. Right. So all I've done so far . Why did that not work? I should have printed. Try that again. There we go. Work that time. Right. So all we've done, we've loaded in the training data using this text data set from directory utility. We've said carve off 20% of it to be validation data. Give me the rest as my training data. And then just so you can see what's happening, to print what label 0 corresponds to and what label 1 corresponds to. And you can see here it said, right, label 0 corresponds to neg. So that's the, that's this folder, the neg folder. So these will all be given label 0, and the pos folder, these will all be given a label of 1. So it's done all that for us, so we don't have to do it. And that's the advantage of using this utility, is it'll do that automatically. As long as you've got your text files set up in that structure, so you could replace those text files with whatever you like. And as long as you keep your training and test data separate and your positive and negative example separate, it'll do all this for you. So that's what we've done there. Now we're going to set up our validation set. And remember that that's going to be 20% of what we've carved off up above. So we called that raw train DS. I'm going to call this raw val DS. So again, I do exactly the same as I did before. It's in the same folder. It's in the training folder, remember, because it's part of the training data. The batch size, same as before. The validation split is the same as before. We're saying, yeah, it's the 20%. But this time I want stored in here, I want the validation bit. So the 20% you carved off, that's what I want in here. So up here, I'm saying exactly the same thing. It's just I'm saying I'm referring to give me the 80% that's the training bit. And here I'm saying, give me the 20% that's the validation bit and store that here. So now we've got a training data set here that's 80% of our training data, and a validation set here, which is 20% of our training data. So we've done our training and validation sets. We set those up. We just need to do our test set. We're just going to use the test set as is. We don't need to split it up. We don't need a validation set or anything there, so we can just use it exactly as is. So we use the same command, but it's easier this time. We just give the file path, which is the test folder this time, and we give a batch size. We don't need to specify a validation split, that doesn't apply. We don't need, therefore, to specify a subset because we're not splitting this up, and we don't need to specify a seed because we're not randomly shuffling them. And this is why you're using the seed up above, because if you didn't, then the 20% that gets carved off here may be different to the 20% that gets carved off here. That's when you can get overlap. So that's why you hold them in place. So it'll randomly give you 20% here, and then it'll use that here. Okay, so that's all we've done basically, is just set up our training, validation, and test sets. So we've basically loaded them in our data. So we've got them loaded in as text, basically. But remember, first thing that we need to do is to standardize our stuff, because our text is raw text. It's going to be full of capital letters, punctuations, HTML tags, all sorts of rubbish. So we need to get rid of all that first. So, and particularly because, as I say, this is web-based data, because it's IMDb, we're going to need to get rid of these HTML tags as well. So what we're going to do here is I've just written a little function to do this. And I saw a couple of groups do this earlier for the word cloud stuff. It's a good idea if you're going to be doing any sort of cleaning up of your data, just write a little function that does this, so you don't have to do this every time. So I've just called mine custom standardization, and the input that it will take is some input data. So basically you pass in some input data to this function, it'll clean it and then chuck it out the other side. So this function does a few things. First thing it'll do, convert everything to lowercase. We can use one of the TensorFlow strings functions to do that. We'd say tf.strings.lower and give it the data we want to make lowercase, and that will make everything lowercase. So then we've got this stored in lowercase. So now we've got whatever data we've put in is now converted to lowercase, and it's stored here. Then I'm going to strip out the HTML tags. Now in this data, the only HTML tags are line break tags. So that's the only ones we need to worry about. This is one of the regular expression things. I'm not going to go into detail about it other than to say, copy and paste this. But basically what this is saying is take this as your input, which remember is the lowercase text that we just made up above, and basically translate this tag into this tag. Okay, so wherever you see a line break tag, replace it with a space. Okay, so it'll essentially remove them. So then that will store that in stripped HTML. So now in here, we've got lowercase text that has been stripped of HTML tags. And then we then want to strip out the punctuation. And this is where we get into a little bit more of the complex regular expressions. Again, I'm not going to go into it other than to say what this will do. You pass in this, the latest one, which is stripped, is lowercase and stripped of its HTML tags. And you basically use this command to tell it to remove punctuation. Just copy and paste that will work. Okay. Again, if you want to get into regular expressions, there's lots of materials out there on it. I hate them, as a lot of people do. Spacey incidentally has, if you're using Spacey, it's got a much nicer way in which you can write regular expressions that aren't so horrible. But for now, just that's how you can do it. Okay. So that function is just, if we pass in some data, some text data, it'll put everything into lowercase, it'll strip out any line break tags, and it'll remove any punctuation. So that'll help us. Okay. So once we've got our data standardized, we haven't done that, we've just written the function. What we're going to do next is set up something known as a text vectorization layer. Ready for when we build our neural network. So we're going to set up a layer that's ready for our neural network. Now remember, vectorization is the process in which we convert our text into numbers, because we have to use numbers. So this text vectorization layer will do all the stuff about converting things into numbers according to their inverse frequency, etc. Now we're going to set up a couple things to pass into that as well. We're going to set up the maximum number of features, or these are basically the maximum number of words that you use. So that's 10,000 different words or tokens. That'll basically take the 10,000 most common words. And our sequence length, which is basically the longest review length that we will take. Remember, they all have to be the same size when they go through the neural network. So this basically says a 200, well, it's not quite a 250 word review, because it's not, all the stop words will be removed and words will be stemmed, etc. as well. So it's not quite 250, but it's 250-ish words. So anything longer than that will get chopped off. We will only look at the first 250. Anything shorter than that, it'll be padded out with a value of 0. So here's where we set up the layer, the vectorization layer. So we set that up as a new text vectorization layer. Now remember, we imported this at the top. Where is it? Here we go. So we imported that so we can, because Keras has got this built in, so we don't have to define what one of these things does. And this will do all the magic for us, all the stuff that I was talking about, if we pass it some information. So it needs to know how to standardize it, so how to clean up the text first. We've written that function up here. We call it custom standardization. So I can say to standardize it, use that function. So you give the name of the function here, and it'll just run that function every time it needs to standardize the data first. The maximum number of tokens is the max features, so only take the 10,000 most common words. The output mode equals int basically just means turn the text into integer numbers. You could have sort of floating point numbers and stuff, but integer is the most common way in which it's represented. And the output sequence length is the sequence length that I set up here. So that basically means just take sequences that are no longer than 250 words. So everything will be 250 words. If it's longer, it'll chop it off. If it's shorter, it'll pad it out. So we've just set up a layer ready that will do all this for us. So where it gets a little bit more complex. So what we want to do here, we need to start this process of mapping our text into numbers. The first thing we want to do is to extract just the review text, i.e. not the labels as well, so not the ones and zeros that indicate whether it's a positive or negative review. We just want to grab out the review text, because that's the stuff that we're going to need to map across using this vectorization. Because obviously the numbers are numbers as ones and zeros, that's fine. Now the way we do this, we can use a little type of function in Python called a lambda function. Now you won't have seen these, well you might have, but certainly not in this course. Lambda functions, they're like little mini disposable functions. So usually when you write a function like up here, you write a series of things that it will do, and its input and its output, etc. A lambda function is basically just a quick and dirty thing. You just want to quickly do something and then chuck it away. Okay, so what this lambda function is doing up here, where it says lambda xy colon x, that's basically saying, give me an x and a y, and just I'll give you an x and a y, and I want you to just give me back x. Okay, so if we were to give it the reviews alongside their labels, then this will say, just give me back the reviews. I don't want the labels. So it's just a little disposable function. They can be quite handy for stuff like this, where you just need it to quickly do something like that. So what we're doing here is we're going to use the map function on the raw training data set to tell it to map the words we've got in our reviews, but not the label. So the input is going to be the result of this function, this mini function, which will just give us back. It'll take the it'll take the, I don't know why that's highlighted. Sorry, I can't turn that off. I'll do that. It'll take the reviews and the labels, and it'll just get rid of the labels and just give us back the reviews, and then it'll apply this mapping function, and it'll store that in train text, and then we can adapt this here using our vectorized layer. Now this is the one we set up above, and we call the adapt method on one of these text vectorization layers. and we feed in this training text. So basically what we're doing, this is a quite complex way of saying what we're doing, we're taking the reviews in the training data, we're chucking away well, not chucking away, we're just ignore the labels for a minute. Let's just grab out the review text themselves and feed them through this thing, the vectorized layer, and do that so that the vectorized layer adapts to this training text. Now, do you remember when we talked about in the machine learning module, we talked about how you when you sort of normalize and standardize, and how you standardize. When you're standardizing, you tend to standardize based on the training data, and you don't standardize on the test data. So you standardize on the data it's going to see, and then use that scale for your predictions and for checking against the test data. This is the same thing. You're giving it the training text, and you're using that to adapt, to work out word frequencies and stuff like that, okay? So you're using the training text to do that. So it'll adapt this vectorization layer to the training text. So it can seem a little bit complex, but basically that's what you're doing. You're grabbing out the review text from the training data, and then you're reshaping this this layer here, which is going to turn your text into numbers, and you're getting it to adapt to whatever your training text, what words are in the training text. So it'll be based on that. Again, don't worry if you don't understand this the first time around. There's lots of words here that will help you understand that. And that is a bit more complex. So once we've done that, we're going to create a little function here that applies the vectorized layer, this one that we've created up above, to pre-process the data. Again, don't worry too much about this. Basically what this is going to do, we've defined a little function called vectorized text. It's going to take as its inputs text and labels. So in other words, review and whether it's positive or negative, 0 or 1. It'll then expand the dimensions using the TensorFlow method, expand dims. What it's basically doing is reshaping the tensor so that it can fit into this. Again, don't worry too much about this. Remember, the tensor is just the shape that your neural network needs in order for your numbers to be in order for it to work. This will basically expand the dimensions into multiple dimensions so that it's in the right shape to go through this. Okay, again, just copy and paste. This will work. You will do this every time. So what it will do is it'll return the labels as they are, but the text having gone through this vectorization layer. So when you call that method with some text and a label, it'll return the text, but it'll call this method, which it'll use this layer, which remember is going to also call this method up above, which will remove, put everything in lowercase, remove the HTML tags and the punctuation, etc. It'll truncate things to 250 words. It'll pad things out. It'll only take the 10,000 most common. It'll convert all the words to integers. It's going to do all that. That's going to set things in motion, and it'll return that alongside the labels. Okay, but it'll do so in the shape of tensor that it needs. So once we've done that, we can then apply, essentially use the map method on our data sets to then, because we've reshaped everything according to our training text, we can now use that to map all three training set data, all three data sets. Remember, we've got a training data set, we've got a validation data set, and a test data set. So we've adapted the way in which we're going to generate the numbers according to the training data. We shouldn't do that on the test data. We should just do it on the training data. But then we're going to apply the way in which it does that to all three. So all three will be essentially scaled in the same way as the training data. So if that sounds a bit confusing, think back to the standardization example in the machine learning module where we talked about when you're standardizing data, you basically, where you're you turn everything into a scale where the mean is 0 and the standard deviation is 1, and you do that on the training data, and then but you don't do it on the test data, but you use the same scale on the test data. So you use the training data scale for the test data, and basically this is just a more complex version of that. That's what that's doing. So that's all your pre-processing stuff then done. So basically this will vectorize the text. It's just we've had to go through a series of steps in order to do that. But essentially all we've done is loaded in the data, and we've used this text data set from directory utility to allow us to do that easily. So we've loaded in the data, we split our training data, carved 20% of it to be a validation set that it can peek at as it's learning. We've set up a little function here that will standardize our data in terms of, getting rid of the capital letters and all the stuff like that. And then we've used that to set up a vectorization layer that will turn our text into numbers, and we specified the options for how many words and stuff we want in that, and the length of reviews. And then we've adapted, kind of reshaped stuff according to our training data, and then applied that to all three. Okay, so by this point, we've now got all of our training data and our validation data and our test data are all now represented as numbers, and the way in which it's done that is based on the training data. So I've stored these as separate data sets. That's good practice to do that. So I've called these original ones the raw training data set, the raw validation, so we can refer back to those if we need them. So that will be them raw, as in the text that's been read in, but these will be numbers, and there'll be numbers in the shape of tensors that we need to push through a neural network. So these are all ready to go. Now we come on to build the neural network. Now this should look much more familiar to you, because this will be exactly as pretty much exactly as you did before. We'll use a few different types of layers here, but the same principles that you saw before in the machine learning stuff. So we're going to set up a neural network. I'm going to set it up as a sequential neural network. Basically means we just build it up one layer at a time. The embedding dimensions here is just I've given it a value of 16. That just basically means that all the hidden layers, remember they're the ones in the middle, will have 16 nodes. Okay. So we set up our neural network model. We do it a layer at a time. So I say I want a neural network, and here are the layers that I want in this order. I'm going to have an embedding layer as the first one. So the embedding layer is the one which will basically get it'll transform your numbers that we've converted our text from into numbers. It'll convert that into the tensors that will go through the neural network. We'll then have a dropout layer, which so I think when you looked at Mike's examples, you specified dropout a little bit differently. You can also include dropout layers, so you can have a separate layer within a neural network that says randomly switch off 20% of the incoming connections, and that does the same thing, same purpose as we did we saw last time, which is you're trying to avoid overfitting, so you just randomly switch off certain things each time so that it doesn't get too hung up on all the details of the training set. So we've just got 20%. Again, that's something you might want to play with. I think in the last session you looked at varying that between 20% and 50%, for example. Usually that's about the range you're looking at. Then we've got something called a global average pooling 1D layer, which sounds very fancy. And I'm not going to try and explain it other than what I've done here, which is basically what it does is it squashes. Imagine your tensor as a kind of blob of jelly. And what this will do, the global average pooling 1D layer, is it just squashes it down into one dimension. Now you might say, why on earth would you do that? And it's basically to just try and remove some of the complexity. And remember from the other lectures we talked about, where in machine learning, you tend to want to try and remove complexity to avoid overfitting, because the less data you've got, the less potential to overfit. So this is quite a handy little layer that you can put in that will basically squash things down. Then we're going to have another dropout layer, and then the final layer here will be just a normal densely connected layer. So you've got an embedding layer that will get it in the right shape, and then it'll be followed by a dropout layer. It will randomly switch off 20% of the connections. Then this kind of squashy jelly thing layer that does this thing that puts everything down into one dimension. It's always difficult when you're thinking in multi-dimensional space. Then another dropout layer, and then finally a densely connected layer. Okay, and that's not going to be the output layer. Well, it is here, but I'll come back to that's not what we're going to use as our output layer. So let me run all of that so far, because we'll print a summary of the model up to that point. Okay, so this is the model we've built. We've got an embedding layer, we've got a dropout layer, and we've got this squishy layer. I think that's what they should call it. And then a dropout layer, and then a densely connected layer. Okay. So all of these have got 16 nodes apart from the final one. Okay. So if you can imagine drawing a picture where you got, and they're all densely connected. So all of the ones from one layer are connected to all of the ones from the previous layer. Oh, right, where am I? Here we go. Right, so that's what we've done. So we've built the model. That's all we actually need to do to build it. All of that rubbish up above, that's just the pre-processing stuff. So as we saw last time, pre-processing, getting your data in the right shape is usually half the battle. And it's just a little bit more complex with text because you've got to get it into numbers in a meaningful way. And so that's what this does, basically. Hello, yes, we've got a question.
In your folders, under your training data, just have neg and pos.
Yes, neg and pos, that's right, yeah.
Okay, because some of us have also got a folder for what I think are neutral ones.
For what, sorry?
We've also got another subfolder.
Oh, I don't know why that's the case.
I think it's neutral ones.
Sorry,
I'm getting more files when I run the code.
Okay, yeah, I seem to vaguely, sorry, you're cutting out a little bit, but I think I caught you. I seem to remember we had this issue with a couple of people last year. If you've got anything other than that, just delete those folders. Okay, that's all you should have. I'm going to blame Windows because it doesn't happen on Linux. So there's something weird going on, but all you should need is neg and pos. And in fact, I think if you don't remove them, you'll run into problems because it'll then try and give, it'll think there's another label. So yeah, if you've got any other folders, just other than neg and pos in these subfolders, delete them. You can leave these text files, that's fine. That's supposed to be there. Although I don't think they do anything for this, but yeah, if you've got any other subfolders, just delete them. I remember this happening before. I'm not sure why. Just blame Windows, shall we? Okay, thank you. No, that was. I'm glad you reminded me of that. I forgot we had that little nightmare last year. Okay, so that's basically how we've built the model. Very no, that's not how we built the model. I haven't got to that. That's how we built the model. There we go. That's it. That's what we do. Now, obviously, you may set up your neural network differently. This is taken from, and I've put the link to the tutorial. This is largely based on the TensorFlow tutorial on sentiment analysis. So this is the way they set it up. But of course, one of the things you'll play around with is trying different structures and seeing what works. So now we've built the model, we need to compile it. So we need to specify 3 things. We need to specify the optimizer, the loss function, and the metrics. So let's just remind ourselves of the optimizer. If you remember back to the machine learning stuff, we said the optimizer is basically some sort of algorithm that's the one that's going to go through. And remember, when it goes through and it checks itself to see what outputs it gets, because it's a labeled data set, it can compare the outputs that it's got versus what the actual answer is, see how wrong it is. And based on that, it'll think, okay, I was quite wrong there. Which of you, it'll look back at its network, it'll look back at its weights and say, which of you caused me that problem? Why did I get the error? Did you contribute to the error? And it'll work out who contributed most. So it'll adjust its weights and learning rate, etc. So it'll go back and adjust itself. And the way it does that is via the optimizer algorithm. And I think Mike said in his lecture, and it's good advice, if in doubt, use Adam. Adam is the one of the most commonly used optimizers now. So optimizer equals Adam is pretty much what you'll always write there. And then you've got a loss function. That's basically the way in which it will calculate that difference between what it gets and the correct answer. We're using a binary cross entropy loss function here. Binary because we've got 2 classifications, positive or negative. And cross entropy because we're dealing with probabilities, because it essentially measures the distance between probability distributions, so the correct classification and the prediction. So binary cross entropy, when you're doing stuff like this, so for sentiment analysis, you've usually got 2, unless you're doing neutral as well, in which case binary cross entropy is the way to go. Now, from logits equals true basically just means normalize the outputs from this one so that they're between 0 and 1. I'll come back to that and how we do that a little bit differently in a moment. But at the moment, this is our output layer, so we need a value between 0 and 1 because we need a probability. So that's the way we can turn that on. And our metrics, we're just going to use, for simplicity, we'll just use accuracy at the moment, but obviously you can use precision, recall, whatever you like here. So we're going to compile the model, put this thing together with an Adam optimizer, with the binary cross entropy loss function, and we'll just use accuracy as our measure of success. Once we've done that, we just need to train the model. So we're going to train up the model. Remember, that's known as fitting in machine learning terms. We're going to specify 10 epochs. So if our batch size is 32, it'll shunt the data through in sizes of 32. And then once it's done all of the data, that will be 1 epoch. So it'll do that 10 times. We're also going to specify, so when we come to fit the model, remember we use model.fit. We'll start training the model. We store it, I think Mike gave this advice, it's good advice, you store it in this variable we usually call history. That allows us to then look back at that. The things we're going to pass into the model.fit are the training data set. Remember, we call that train DS. Remember, it's not the raw data though, it's the training data that has been vectorized and tidied up. Oops, where am I? There we are. The validation data is the validation data set. Again, it's the data that's been tidied up and vectorized. Number of epochs is 10. I could have put 10 in there, but again, I've separated that out. And verbose equals 1 just means tell me everything you're doing as we go through and do this. Okay. So let's, so once we do that, we'll basically then we can evaluate the model. So we can call the evaluate function on the model using the test data set. So we'll then pass it the test data set, which it hasn't seen before, but we can give it the answers so it can check itself. And we'll look at the level of loss and the level of accuracy, and we'll print that out. So let's run down to that point. So let's get a bit more exciting now. Here we go. Right, so we can see it training. Okay. It may take I've got a fast computer, so it may take a bit longer if you've got a slower computer, just be warned. Okay. But you can see that gradually, so this is the training data accuracy. It's gradually getting better and better as it goes through. So up to epoch 9, up to epoch 10. We've ended up with so the final epoch, we ended up with 91% accuracy on the training data. And then we checked it, the final thing, we checked it on the test data. We got accuracy about 86%. So we've clearly overfitted a little bit because we've got a bit of a discrepancy between the training data and the test data, but it's not a bad first stab, I have to say. And again, if you scroll back through the epochs, on the very first one, it was dreadful, it's about 50%, which is what you'd expect. The weights are random initially, so it's going to be no better than tossing a coin, which is what you're getting. But then very quickly, you start to see it improve as it gradually uses its Adam optimizer to gradually optimize itself. And you can see it starts to get up much higher and we get these much better levels of performance. Okay, scroll back down. So that's all good. So we've trained a model. So we've built a model, we've trained a model on that training data. And we've then tested it on the test data. We're getting about 86% accuracy on the test data, about 91% accuracy on the training data. But of course, the whole purpose of doing this is that we want to use this model, presumably, to look at new raw string sets. We don't just want to use it on the data we've downloaded from this website. We want to use it for anything. So in order to do that, we can export a version of this model. And rather than having to go through because when we give it new data, that new data is going to have new words in it. So we're going to need to do all the vectorization stuff and make sure that's vectorized properly. And we also probably want to bung on at the end a sigmoid activation function, which you saw last time, is a way in which you can make the final layer a sigmoid activation function node, and that will basically convert the output to between 0 and 1, and that can is really useful when we want a probability. So what we're going to do here is we're going to take that model that we've just trained, and we're basically just going to shove onto the start our vectorized layer, that one we set up all the way up here, there. So rather than doing that separately, which is what we've done here, we created that layer and then pushed things through manually. We're going to shove that onto the start of our neural network. So we'll make that part of the neural network. And then we'll put the model that we've just trained in the middle. And then at the end of the final layer, we'll put on this sigmoid activation function. So the new model will be made up of the thing we've just trained, but then bolted onto the start, the vectorization layer. So we don't have to do that manually every time. And then at the end, a sigmoid activation function layer, which will convert our value to between 0 and 1. So that's our exported model. And you can see we've built that in the same way that we built up the previous model, layer by layer. It's just this time, rather than specifying all those layers up here with the embedding, dropout, the squishy squashy, and the dropout and the dense, that's all done now. We've trained that model, so we'll just bung that in as model. So all those layers in the middle, and then the vectorized layer that we set up at the top at the start, and then the sigmoid activation layer at the end. So once we've done that, we've built that model, we then need to compile it, remember, exactly as we did before. We're going to compile it. I'm going to use the Adam optimizer. I'll use the binary cross entropy loss function. This time I'm going to say from logits equals false, because we've now got a sigmoid activation function at the end. So we don't need this thing to manually put them between 0 and 1 to normalize them. We've got the sigmoid function that will do that for us. So we turn that to false. And again, I'm going to use accuracy as the measure. So if I run that again, we get invalid syntax. Of course we do. I've typed something in wrong. Where is that lowercase? Line 113. Ugh. There it is. Ooh, what have I done there? Let's push the undo key. Let's push. There we go. Pushed undo a couple times. That seemed to work. I'm obviously just accidentally copied and pasted something. So again, so we're running the whole code now. We're training our model again, so we can see the accuracy gradually improving and loss gradually reducing, which is what we want. Remember, loss is error, so loss is getting it wrong much less frequently. That's good. It's all stabilizing. Gets to epoch 10. Brilliant. It's obviously a little bit different this time, and then 86% evaluation on the test data. But now we've got that stored as an exported model. So if I wanted to then apply it to other text, I can use this exported model to do that, and it'll bung on this trained model together with the vectorization layer at the start and a sigmoid activation layer at the end. Okay, I realize that was a lot of information to take in. Any questions? And I flag up, I don't expect you to understand all this first time around. Okay, good. Probably exhausted. So I'm just going to mention one quick other thing, which is very easy, and Mike touched on this in the machine learning. So this will be relatively easy because you've seen a little bit of this before. So we saw during our training, if we look back at the training, we saw it starting to stabilize, and we've got lots of big improvements in the training data, and then it started to stabilize a little bit. But then in the validation, if we look at so this is the training data. If we look at the validation data, which is over here, so that's the validation accuracy. Remember, that's its sort of mini test set before it sees the test set. We get some improvements up to here, and then it doesn't really get much better. It stabilizes much more quickly. The training data will just keep getting better and better and better because it's overfitting. Whereas the validation accuracy tends to plateau. Now, we talked in the machine learning module about ways in which you can avoid that, reducing model complexity, etc. One of the ways you can just stop training, basically. Don't run through as many. Maybe you're training for too long, so don't have as many epochs. You could either do that manually and just look and say maybe cut it off at epoch 5, or you can use early stopping, which, as I say, we showed you in the session 7D, and I'll just show you in this code. So I've got a version of this code, SA with own data, early stopping. From line 275 onwards, we've got the different code. The only thing to flag up here is we need to import it. So from tensorflow.keras.callbacks, we import early stopping. If you don't, it'll remind you to do that. So if we go down to line 275, everything above is the same. So here's where we're going to do our early stopping. Remember, this is basically just a nice little feature that Keras has got that basically says, keep an eye on one of the metrics. If you don't get an improvement or you're not getting much of an improvement, then stop. So what this callback's doing here, we're setting up an early stopping callback. We're telling it to monitor the validation accuracy because that's giving us a clue about, because remember the training accuracy is just getting better and better, but the validation accuracy is giving us a clue about what this might be like more generally, because it's not training on that, it's just peeking at it every now and then. And so we're telling it to monitor the validation accuracy. The min delta is the minimum amount that we want to see a change. So here we want to see at least a 0.01 change. And I've set up quite a low patience here. Patience is basically the number of epochs that you will wait. So if you get, if the validation accuracy doesn't improve by this much within this amount of time, then stop. Because you've plateaued basically. So you can change that. So you might be a bit more generous and say, well, give it a few more epochs to try and improve. You might say, I want to see a bigger improvement. So you might get a bit more harsh, and you can play around with these things. And then basically once we've done that, we just run everything as we did before. It's just that when we fit the model, when we train it, we add in this early stopping callback. And then we can see how that improves things. So let's have a look. Let's run that code here with the early stopping and see if that helps. So let's run that. Here we go. So right, now remember, it shouldn't go to all 10 epochs now because it's going to stop once the validation accuracy doesn't improve by at least 0.01. Let's see what happens. There we go. So it's stopped after 5 epochs. Now, it hasn't really helped our accuracy. In fact, it's made things a little bit worse here. Training accuracy only got up to 84%, but it has removed the distance between them. So we're clearly not overfitting now, but maybe we haven't gone quite far enough. So we may need to play around with the patience and the change. I've been quite harsh there in terms of when I wanted to cut off. And like I say, it's not just that. You may want to look at your model complexity and all sorts of other aspects as well. Okay, I'm going to stop rabbiting on, and I'm going to give you, first of all, a chance to have a break. So I'd recommend you take at least 5-10 minutes to have a break. And then I'm going to give you an exercise to do. So what I want you to do is to create a CSV file called x1reviews.csv. And basically in that file, I want you to write a small sample of very short movie reviews. Just make them up, or based on reviews that you've of films that you like, or even just grab some from IMDb if you want. Just be careful of formatting and stuff. But just have a few, like 3 or 4, 5 sample reviews, and basically just have a new review on each line. Okay. Make sure that file is saved in the same folder as wherever you're going to do your PyCode. Then what I want you to do is take a copy of that file we've just looked at, SA with own data, early stopping, and I want you to add some functionality in your groups to the end of the code that does this, that it'll read in the reviews in the CSV file that you've created, and it'll store those reviews in a list, and then it'll iterate through that list of new reviews, and then for each review, it will apply the exported model that you trained earlier in the code to the review. So that model that we shunted together, the trained model, we bunged on the vectorization layer at the start and the sigmoid activation layer at the end. So apply that model to this new review, the one you just made up, each new review. And then for each review, apply that model to get a prediction. And what I want you to do is then get it to print a copy of the review text. So whatever the review says, so maybe your review says, this movie was a load of rubbish. I want you to print out, this movie is a load of rubbish, so whatever the review text is, along with the predicted sentiment for the review based on what this trained model, this pre-trained model that we train up here, outputs. and according to one of these 4 categories. So if the output value, remember you got the sigmoid activation function will give a value between 0 and 1. If that value is less than 0.25, then call that a confident negative and print out that it's a confident negative. If it's between 0.25 and 0.5, so it's a possible negative. 0.5 to 0.75, print that it's a possible positive, and a 0.75 to 1 is a confident positive. Okay, and also print the raw output. So you're basically iterating through, you're reading in your CSV file with your reviews that you've made up, and then you're going to iterate through a loop. And then for each review, you read in the review, obviously each review in that list, you apply the model to make a prediction on that review. And then you print alongside that, here's the review text, the model predicts it is a confident negative, possible negative, whatever it is, and here's the output score. Okay. Now, a couple of things to mention on this. First, when you're reading in from a CSV, each row is going to be a list of comma separated entries, even if the row has just one entry. So if you've got a single review on each line, it will still be stored in a list at position row square bracket 0. So just remember that, that'll come in handy when you read them in. And the bit I haven't told you yet, but this is the crucial bit, to generate predictions using your model, once you've trained the model, we need to call the predict method on the exported model, and then we feed in the reviews as a list of strings. Even if you're just predicting one review at a time, you still have to pass it in as a list, but that list just contains a single review. So then if you call the predict method and pass it in a list of strings, even if that's just one review, it'll then return a list of output values. That's the outputs from the sigmoid activation function. So if you've just passed in one review, it'll pass out a number between 0 and 1 that will represent its prediction. So the closer it is to 1, the more likely it thinks it is to be positive. So those are essentially your probabilities that it's outputting. So I want you to play around to do that, and then try playing around with the model, try changing the number of epochs, adding another hidden layer to the network, maybe changing the number of hidden units, try changing the batch size. Be a bit careful with some of this though, especially things like batch size. If you make it too small, your compute time, unless you've got a very, very fast computer, is going to significantly increase. Change the training and validation split, play around with some of the stuff we talked about. Have a look at playing with the number of words that you're using. So we got at the moment 10,000 most common. Play around with that. Try different review lengths. So at the moment we've got 250 words, etc. And then try writing some mixed reviews too, where you're saying both positive and negative things, and have a look at how well it performs. So see if you can get it, how well you can get it to perform on your new made up reviews. Work in your groups. The code itself shouldn't take too long. Okay, you should be able to do this fairly easily. Just follow that step by step. It's not much complex code I'm asking you to do on this. The main thing I want you to do is start playing around with it and seeing what you can get out of it. So I'm going to give you a little bit less. Well, actually no. Let's resume. We'll resume at 4 o'clock. So I'll give you a chance to have a bit of a break as well. So stretch your legs for 5-10 minutes, and then get back in your groups and have a go at this. So add in this bit of code to the end. Remember to take a copy of this this file first. Add this code on the end that will do this. And write some reviews and see what happens and play around with it. Okay, right, I'll stop sharing and I'll open up the rooms, but go and stretch your legs because that was a lot. Oh, sorry, there's a question. Or was that just a hand up from earlier? Sorry, it's you, Andrew.
Right.
Oh, okay, no worries. Okay, cool. I will stop sharing there and I'll open up breakout rooms. Hi everyone. Okay, so I thought I'd stop you there. I know a few of you are a little bit further behind. Some managed to get nearly there, and a couple managed to get it all working. But there was just a couple more minor things I wanted to go through just before we close off. I won't be able to have time to go through the code, but obviously you can look through that in your own time. But at least if I talk through the principles, I thought that might be quite useful. But hopefully it's given you a bit of a chance to just have a play around with this. And as I said earlier, don't be too put off. It will gradually make sense, and the more you look back through with fresh eyes, and have a look back through this stuff. Hopefully it'll gradually make more sense. I'll just very quickly share the solution that I had, just so you can see it working, because it leads on to quite neatly the last thing I wanted to talk about. Where am I? Spider. Okay, so obviously you may have done this in different ways. I suggested doing it as a CSV file. You don't have to do that. There's loads of different ways you could do it. You might, for example, just have them in separate text files, much as you did when training the model, and then just read in the whole of the text file, and then store each of those entries as a string in a list. You could do it that way. However you want to get the information in is absolutely fine. But I just gave you the CSV nudge because that's you're used to using and reading in from CSV files. So I thought that'd be the easiest, most familiar thing to do anyway. So all I've done, I've just set up a brand new list. I've just called list of new reviews. I open that. I set up a new CSV reader. I need to import the CSV at the top as well, CSV library, and then I'm just going to go through each row in the reader, and I'll read in that row and it's the position. Even though there's only one review on each line, I still need to say it's at index 0, even though there is only an index 0. So if I just show you, here's my 5 entries basically. The movie was extremely exciting from beginning to end. I loved every minute. This was a disaster, poor storytelling, etc. So I've got 6 reviews that I've put in there. So once we've got that read in, I'll then have a list of new reviews in here, and then I'll iterate through. So you can do this in different ways. You can just chuck in the list of reviews and it will give you back a list of predictions in terms of the probabilities of them being positive or negative. The probabilities of them being positive, I should say. Or you can do what I've done here, which is basically you go through each review in a for loop, and then I've just called the predict method on that review. I still have to pass it in as a list, even if I'm doing that. And then I can just print the review and the predicted sentiment, and say whether I think it's confident, negative, possible negative, etc. I will just, no, I can't do that because I'm in the wrong folder. Sorry. That's because the solution needs to be out here. Let me just open that back up. And now run it. There we go. I'll run it very quickly because my machine's fast. I know a number of you are having severe issues running this stuff. So this is where you do need fast computers if you're doing anything meaningful with it, because it can take a long time. One tip, if you did, so mine's done. I spent a lot of money on this computer, and that's why. But you will find, apologies for the Windows issue, I completely forgot we had that nightmare last year. If you don't remove those extra folders, it seems to be only in the training folder. There's a new folder that it puts in called unsup, which contains 50,000 files. If you don't remove that, not only will your training take about 2 years, but your training performance will be dreadful. It'll be about 10% accuracy. It's because it's got, I don't know why it's doing it. It's doing something really weird. It goes back to Mike's point that everybody uses Linux for this. So the problem is that when somebody does something on Linux and then it works, they just dump it out there, and good luck trying to get support for anything else. So fortunately, it does work as long as you remove that folder, which I don't know why it's added. If you delete that, it'll work fine. And I must have a look at why it does that. It's obviously something weird going on. But anyway, I've trained that, and then I can have a look at my reviews. So this is just stuff that I've made up. I've just typed these, and it predicts whether it's a possible positive or possible negative or whatever it may be. So this first one, on my reviews, it tends to be more confident about negatives than it is positives, but it's predicted that one's positive. This one's a negative, that all looks good. This one's a possible positive, a bit more confident about that. That one is a possible negative, which seems to be, they thought it was okay, but they didn't like it that much. Best film I've ever watched, again, possible positives, not too confident on that, even that's quite strong. And one of the groups actually found when they used some reviews from IMDb that were longer, that they were getting much better results. So they were getting stronger confidence in terms of the results. These with very short reviews, obviously it's got far less to go on, so you'll tend to get a little bit of uncertainty, which is why you're getting a lot of figures around the 0.5 mark generally, unless it obviously in this it's picked out enough that it can be quite confident about the negativity. I put this one in deliberately. The acting was great, the special effects were rubbish. It's predicted that as a possible negative, but it's very close to 0.5. Now, this is a really good example that leads on to the final point I just want to make before we close off, which is around mixed reviews. So let me just bring up the slides. So I won't have time to go through the code, but the code is there for you to look at how to possibly do this. So let's take an example. Let's imagine we're using our sentiment analysis to look at some patient survey data, which may be something that you will do. So if we imagine somebody's written, the care from the staff was absolutely fantastic. They made me feel safe and nothing was too much trouble. But when I was discharged, I had to wait over 5 hours for my prescribed medications at the pharmacy. This is atrocious. Now, that's exactly the kind of review that you might see. That people won't necessarily just be talking very positively or very negatively about all aspects of the care or the service. So what's very clear in this review is there are both positive and negative elements to the above. Now, how might we deal with this? If we were to consider this review as a whole, if we were to say, I think it's positive, then essentially we're making the assumption that the care from the staff was more important to the reviewer than the wait at the pharmacy. Now, that may well be true, but we don't know. We're assuming that. On the other hand, if we were to say that this is a negative review, then we're basically assuming the opposite. We're assuming that the wait at the pharmacy was more important, the thing they didn't like, that was more important to the reviewer than the care from the staff. So you might say, well, what if we were to rate it as neutral? But that in itself can be a problem. Because if we're rating it as neutral, then essentially what we're doing is we're assuming that both aspects, the care they received and the wait at the pharmacy, are weighted equally by the reviewer, and essentially that their overall feelings, therefore, about their stay are neither positive nor negative. But that's an assumption too. That may well not be true. In fact, in a lot of cases, it won't be. They'll likely have an overall feeling of positivity or negativity. So what can we do about that? Now, there's two ways you can approach this. One is you can have a dual output to your sentiment analysis. So rather than having as your final output layer a single node, which has a sigmoid activation function that gives a number between 0 and 1, and that predicts whether it's positive or negative, you can set up a neural network that has two output nodes, and each one of those has a sigmoid activation, and it will predict whether it is both positive and negative, and that's known as a multi-label model, something we mentioned in the very first session of the machine learning module. Now that's fine, and that can be quite useful if your question is what are, how many people are saying things are positive, how many people are saying things are negative. But in reality, you're probably wanting to understand more than how many people are saying positive things and how many people are saying negative things. You're probably wanting to also understand what they're saying, because you probably want to do something about it if the things are bad, or indeed if things are good, and you want to make sure those things continue. So another approach is we can break down the review into individual aspects. So in that example review, there'll be two aspects: the care from the staff and the wait at the pharmacy. And we can analyze the sentiment of those individual aspects instead. And this is something known as aspect level sentiment analysis. And so this can be really useful when we're just trying to understand, okay, there are mixed things that people are talking about. Can we break this down further and get them to and apply our sentiment analysis so that we can understand what they feel positively about and what they feel negatively about? So the key difference basically with aspect level sentiment analysis is that we need to split our text into different aspects first. And then once we've done that, we can just analyze sentiment in the same way that we would for any text. So if we imagine this block of text here, somebody's written this review. I tried to get through using the supplied telephone number first, but nobody answered after 10 minutes, so I gave up. I then decided to go to the surgery in person, but I was waiting for ages here too. The receptionist I eventually spoke to was very rude. When I finally saw a nurse, she was incredibly helpful and put my mind at ease. I thought the coffee from the coffee machine was excellent too. Makes a change. So that's a mixed review, and they're talking about lots of different aspects of the service they've received. So what we could do is identify, in fact, there are arguably 5 different aspects of this review. There's the wait trying to get through on the telephone. There's the wait when attending the surgery in person. There's the rudeness of the receptionist. There was the helpfulness of the nurse and the quality of the coffee from the coffee machine. And they feel differently about these different things. Some of them they feel very negatively about, some very positively. So one approach might be to try and identify and break down automatically what the different aspects of a review or a piece of text might be. And one way we can do this is to look for our good old friends noun phrases, which are also known, by the way, in natural language circles as noun chunks. So you will often hear about chunking, and that basically means separating into noun chunks. Now, noun phrases are, remember, phrases that have a noun as their head and the describing words around that noun. So my fluffy cat, or the cat who ate all the tuna, are noun phrases. I'm not going to get you to do this, but if we imagine what the look at what the this example review we've got, and if we were then to try and identify what the noun phrases were, here are the noun phrases. So we've got the supplied telephone number, 10 minutes, the surgery, the receptionist I eventually spoke to, a nurse, my mind, and the coffee from their coffee machine. So actually, if we compare those noun phrases that we identify to the various different aspects, there's not a bad match between these various different aspects. So by identifying noun phrases, that might give us a clue about some of the different things that people are talking about. So one approach is that we can look for noun phrases as a clue to what some of our aspects, different aspects in a particular review might be. And then we could look for those noun phrases and then apply our pre-trained model to those sentences that contain the identified noun phrases, so that we're getting a sentence level sentiment analysis to say when people are talking about the coffee machine, we predict they're talking positively or negatively, etc. Now, fortunately, Spacey's got built-in functionality to do it. When we do that magic command, as you saw this morning, where we say article equals NLP raw read, which is basically telling Spacey to do its magic, and we used that this morning just to look at the named entities it predicted. It's doing all sorts of other stuff as well, and we saw you saw that it was also breaking it up into sentences and storing that, but it's doing all sorts of other parsing stuff. And one of the things that it does is it automatically identifies noun chunks for you, and it stores that in article.noun chunks. And so you can just look at article.noun chunks and it'll show you what the predicted noun chunks are for this particular text. So I'm not going to go through, because we're nearly at the end of the session, how we would do that, but I'll show you the code file that you can look at. So it's aspect level sa.py, and this basically will combine what you've just done in this afternoon session, all the sentiment analysis stuff, all that you're probably hating at the moment. But after it's done that and it's trained up the model, it will then do some Spacey stuff. So it'll load the NCore WebSM model here. Obviously, you can use whatever model you like. And then it's going to set up a dictionary of noun chunks. And we'll have a little review index. And basically, it'll go through each review that we've got, that I put in here, for example. And it'll apply the NLP. Remember, that's the language that is derived from that model, the Spacey language. So it'll apply that. Spacey will do its magic on that review. That means that we can then get out the noun chunks for that review. And then we can append those noun chunks for that review to that list of noun chunks for this particular review. And then we can set that up against the review number and then add another thing. So if I just run this very quickly, so I've got the benefit this runs very quickly on my machine. So we're training the model exactly the same as we did before, and I've put in the same added reviews that I did before. Let's see what happens. Here we go. So I've added this bit in now where it's saying for each review what the predicted noun chunks were. Now, some of these are going to be a little bit odd because they're going to be saying, so it's identified the noun chunk this, and it's picked it up from this was, and that's in the sentence, this was a disaster, poor storytelling, and it's predicted that sentence to be a confident negative, which I would agree with. And obviously a disaster falls in the same sentence. So you may want to do something about duplicates, but it gives you a sense about ways in which you might want to approach this, and you probably want to refine it in some way. But if we look back to the problem one, which was the last review here, where we said the acting was great, but the special effects were rubbish, it's picked out two noun phrases, picked out the acting and the special effects, and therefore it's treating those sentences where it's picked out these noun phrases, and it's looking at those sentences individually. So it first looks at the sentence, the acting was great. It predicts that to be a possible positive. So it's rated that one's positive. And the special effects, where it says the special effects were rubbish, it predicts that sentence to be a possible negative, which is good. So essentially what we've done is we've managed to improve, just for a very crude implementation, we've managed to get this review, which was I can't even remember how it was predicted before, whether it was slightly, I think it was slightly negative. They predicted 0.48, I think, but it was so close to the middle that you could see it was uncertain. Now what it's done is it's broken this down into, I'm not just going to say it's negative, I'm going to say part of it was positive and part of it was negative. And that might be really useful, because if you imagine this review was the care was fantastic, the wait at the pharmacy was terrible, then suddenly you've got some more information. You've automatically been able to break that down and apply your sentiment analysis and identify certain aspects that are talked about positively and certain aspects that are talked about negatively. And you can even combine that with a named entity recognition as well. If you wanted to pick out, certain people or places or procedures, for example, that people are talking about positively or negatively, you could do that using the same approach. Okay, I'll stop talking because I realise this afternoon's been a very intense session, so I do apologise. I hope it hasn't put your sentiment analysis, because there's actually some really good stuff that you can do with this, as Mike Hill demonstrated amply last year and did an absolutely amazing project based on this, and knows far more about Twitter sentiment analysis than I could, and he's going to be one of the mentors this year as well. So if you are interested in this, I'd encourage you to have a look at it, and don't be put off by this, as you will get it. It just appears a bit, it's a bit more complex on first glance, because you're having to do the extra text-based stuff to get it in the right format for your neural network. But once you've got through that, you can see actually you can do some really, really good stuff with this. And obviously in the wild, you would be looking at other data sets, not just the IMDb data set, the other pre-trained model. And a question that came up in one of the groups earlier, and something I didn't really mention, but is in your code. There is a section of your code. It's where I build the model. Here we go. So there's a bit in here that I skipped over. So when we built up that model, we put in this embedding layer here. Now, this is just basically, we're building that up as a fresh new embedding layer that hasn't been pre-trained. So basically what this means is this model at the start knows nothing. And then it's learning from scratch everything based on the IMDb data that we give it. But you can do something known as transfer learning, which is highly recommended, which is basically, rather than starting from scratch, you start with a pre-trained model that's already been trained on common words and common things that it would expect to see. So it does all that initial work for you. And then on top of that, you start with that and then build on your training from there. So then if you were doing, movie reviews, you can bung on your IMDb stuff on the top. And generally speaking, transfer learning works much better, because it's not having to spend all that time originally just trying to learn really common words that it can see anywhere. It learns that at the start in this pre-trained model, and then you shove that in and start, rather than starting from scratch, you can start with a pre-trained model and build from there. So then if you wanted to train it on, your patient notes or whatever it may be, you can then start with the transfer learning, start with the pre-trained model, you then use transfer learning to then say, right, and now I want to train on some specialist stuff that I need for this. And it can then start to learn some of the nuances in your particular data. And that's a much better approach to take, because if you don't do that, and you're then having to train from scratch every time, you're going to need so much data that you're going to need to feed in to train it in the first place to get good enough. And of course, It's supervised learning, which means you've got to go through all the training data. You'll have to go through manually, and you'll have to say, is this positive? Is this negative? And that has to be done manually for the training data. So you want to try and minimize the amount. You don't really want to be sat there. Well, perhaps you do. Maybe you would enjoy that. But I would imagine most of you don't want to be sat there going through 50,000 patient records or patient surveys and saying this one's positive, this one's negative. That's probably not a good use of your time. So using transfer learning is really good. And you can also use have a look out there for other models that have been pre-trained and load those models first. Stuff that's relevant to your area. People will have done and built models, and you can use those models as your starting point so that you don't have to go through all of that from scratch. And so I put in these comment notes. You can try this out using a pre-trained general model by changing the embedding layer, and you can just remove, it tells you how to do it. You can just remove some of the comments around this and replace a part of the model declaration. It explains how to do that. So you can try that out and see how that works. Okay, I think that's probably enough for today. Are there any questions before we close off? No, good. I probably exhausted you. Okay. Thank you for coming along today. Hope that's been enjoyable. And as I say, if any of you are interested in doing natural language processing projects, I think it's a great area to get into. And there's lots and lots of potential for this stuff. Either as as the focus of your project, or as an aspect of a wider project. I think there's some great stuff, and there's certainly I've got lots of experience in this. And I say we've got Mike, who's our trainee, one of our training mentors, has done a lot of work in this for his HSMA project. So there's some good experience out there to support you. Those of you coming on tomorrow is agent-based simulation day. So all that fancy stuff we did in cellular automaton, and all those great ideas you came up with in that cellular automaton session. Tomorrow we're going to show you how to build using Mesa, which is a really nice Python package and a lot friendlier than this. How to build a really nice agent-based simulation of a disease outbreak, which is nice and timely. And then you're going to have a go at then building your own agent-based simulation using what you've learned. So you can, some of that stuff, I know loads of you had some really good ideas in the cellular automaton session, and you said, if only I could build this. Tomorrow I'll show you how to do it. It's actually pretty easy. Okay, great. I will stop there, and I look forward to seeing you tomorrow. Fantastic. Goodbye now.